on the Zoom chat, and that might be the easiest way to monitor as well. But please don't use the Zoom chat for conversation. We're trying to keep all the conversation on Slack, and we can have clarification questions or discussion happening there. That's fine. We prefer that. And finally, questions and interruptions are absolutely welcome. If you want to, at any point, ask a question, please raise your hand. We'll try to, bring you in as quickly as we can. Otherwise, let's just get started. So here's the plan. Broadly, we are going to talk about, like I said, for the next 3.5 hours. The agenda that you see on the webpage is dated, and it was built for when we thought that you would actually want to go out in the hallways and talk to other people. But here you're going to basically walk into the living room and meet the rest of your family, which you can do afterwards as well. So we are changing the plan here a little bit. We are basically going to break this down into 20-minute pieces. And we are planning to have 18 minutes for each piece and a 2-minute break at the end of each piece so that you can have like a bio break or grab a drink or whatever you want to do. So we'll do 18 minutes, 2 minutes of silence, 18 minutes, 2 minutes of silence. And there is a 20-minute break in the middle there at 3 p.m. EST. So calibrate yourself accordingly. Otherwise, like I said, there are going to be 10 sections. I won't walk through each one of them, but we're going to mix in discussion and theory with demos and things. And there's going to be Q&A, hopefully before the break, a little bit of Q&A before the break, but there's going to be extended Q&A at the end of the session. So that's generally broadly the structure here. And with that, I'm just going to get us started. We're going to introduce ourselves. I'll introduce myself first. I am Jana Iyengar. I work at Fastly. I'm in the CTO's office there. And I'm also in one of the editors of the QUIC specifications at the IETF. I worked on QUIC. I've worked on transport generally since 2000 in academia and at Google and at Fastly now. And I've been working on QUIC since 2013 with Swett and the other folks at Google. And I've continued working on it since then. I also chair the IRTF's Internet Congestion Control Research Group. That's me. Ian, do you want to go next?
Yeah, I've been at Google since around
Muted.
2011.
Can't hear you.
Can people hear me?
Not muted, but can't hear you.
I can hear you.
Yeah. Okay, great. I'll get them. Yeah, I've been an engineer at Google since 2011, mostly working on the QUIC project since 2012. I am also an editor of the IETF QUIC specs. And I also have a particular fondness in my heart for, or at least spent a lot of time on BBR and BBR v2. So I definitely have an interest in a wider area of congestion control and transport than just QUIC.
Right, and I'm Robin Marx. I'm a PhD student from Belgium. I'm in my last year, and I've mainly been looking at the performance aspects of new protocols. First HTTP2, and now, of course, QUIC and HTTP3. A large part of that has been creating tools that help others do similar analysis as well, and that's mainly why I'm here today. I'm going to be mainly demoing some of the tools that you can use to debug QUIC.
Awesome. So I am sorry. I was having some computer troubles here, but for some reason I couldn't hear Ian at all. Can you hear me now? Yep. Okay, lovely. So let's get going. I'm going to start off with just talking about broadly for the first section here, talk about QUIC's intellectual heritage. So people who've tracked any of this work in the past might find some of your favorite pieces of work show up here. The point here is to get you basically a sense for where QUIC comes from. QUIC's in a long line of work, and that's what I'm going to talk about. So first off, what is QUIC? QUIC is simply a new transport protocol, and it is built for today's internet and the modern web. And it's basically trying to go after design spaces that TCP didn't really go after. It's UDP based because UDP gets through most networks today and pretty much nothing else does. Well, UDP and TCP get through networks, but it's hard to build on top of TCP. And QUIC has encryption baked in. It's a fundamental part of QUIC. Encryption, protection, and privacy are super important for QUIC, and then you get it right out of the box. That's just a very high level thing about QUIC. If you heard about HTTP3, or if you've not heard about HTTP3, what is HTTP3? This is simply HTTP running on top of what I just described. So we have a new transport that's all encrypted and everything else, and then we are running HTTP on top of it, and that's what we're calling HTTP3. This happens to have feature parity with HTTP2, except for priorities. And that we're not going to get into the details there, but the point is that HTTP2 had a particular design for priorities that was deemed not, after experience trying to deploy it and using it, was deemed not amazing, and they didn't want to carry it over to HTTP3. And so there's a new scheme that's being devised for both HTTP and HTTP3. So that's HTTP3. So that's just a high level summary. And we're going to dive into the details of these things right now, right? So before we do the details of the protocols themselves, history and intellectual heritage. So I'm going to start off with a quick history. And really this is about Google's QUIC, or Google's version of QUIC, which we now call GQuick, because it is not what we are calling QUIC today. And this confuses a lot of people. So the thing that Google deployed was basically Google built and deployed a protocol for HTTPS transport. And that was starting in 2014. This was deployed between Google services and Chrome. And those are the only entities that use it. And it was eventually expanded to mobile apps as well on the client side. And in 2017, it was about 35% of Google's egress traffic. This was a significant chunk of internet traffic, 7%. And at that point, Google considered the experiment to have been basically a success in that it achieved its ends, and it proved QUIC had proved its mettle. And so Google took the effort and brought it to the IETF so that everybody else could work on it and make it a protocol that could be owned by more than just Google. And that work started in October of 2016. So that is GQuick. Even Google is moving from that to the IETF standard form, and that's what we're going to talk about now. So the QUIC that we started at the IETF has matured significantly over the past 4 years now. There are a number of things that have happened, and we'll talk about some of them today. We won't talk about all of them today, but basically a lot of details of GQuick as they came into the IETF, and then they were worked on by the IETF, changed quite a bit. And all of it has matured QUIC significantly from an experiment to a standard that can be widely used by many, many vendors and developers can build to this. So that's the historical arc of where QUIC was and where it's going. But this ideas that you're going to see in QUIC come in a long line of work on web transport. Web transport has seen work over a large number of years, and I'll do sort of I'll breeze through this a little bit. I have a number of work items to touch on, but I won't go into the details on each one. You might be familiar with some of them. If you're not, you can go up and look them up later. They'll be in the slides. So in terms of HTTP, what are we talking about really? This is the stack we're talking about. There's HTTP sitting on top of TLS, sitting on top of TCP, sitting on top of IP. This is our lovely, wonderfully used and abused HTTPS stack that is widely popular. And the different pieces in here have had different evolution curves, evolution arcs. I'm going to talk first about TCP, which is built for connection. It was built to give you the notion, the users above it, a notion of a connection, give you reliability, protect the network in the sense of keeping the network from collapsing with congestion control, and finally offer an ordered byte stream up to the users of this particular protocol. So TLS and HTTP sitting on top of that could assume that there's this magical connection that would always give you a pipe that would always give you ordered bytes. Now everybody's seen this in their textbooks and everybody's taught this in their classes, and that's what TCP was and is, and that's what it's built to be. Now, a TLS that sits on top of it is supposed to provide authentication encryption to the things that sit above TLS. That's important. Why is that important? We'll come to that when we come back to QUIC. So TLS here sits on top of TCP, doesn't protect TCP, of course, but it protects the thing that's above it. And that's where we thought the most interesting things were. What are the most interesting things here in this particular stack? It's HTTP, a whole bunch of different objects, requests and responses flowing back and forth. And there's a need for latency, low latency. We've always had this need, but it's become much more important in recent times. So that's our stack, right? That's how we stack functions. That's how we've been using this. HTTP starts off with HTTP 1.0. Well, actually, it doesn't start off with 1.0, but I'm going to start this history at 1.0 because you can go back to Gopher and it's not that interesting. So the point here was that HTTP 1.0 was very basic, independent file transfers, one per connection, but you're doing a lot of objects, it becomes a problem. So HTTP 1.1 introduced the notion of connection persistence, where you could do multiple objects over the same connection and also keep the connection alive for subsequent requests and responses to flow on. And pipelining as well, so that you could do multiple objects at the same time, but really that never really took off. I mean, in deployment, there's basically almost nobody who uses pipelining. But that's, HTTP 1.0 and 1.1 happened in the early mid 90s. So you're talking about the 90s here. And eventually around 1998, after a while, there was an effort. I don't know if some of you on this call were definitely around at the time and probably were aware of this stuff, called HTTP NG. Now, this was a W3C effort trying to figure out what the next generation HTTP. This is when the web was starting to explode, right? So there was obviously stuff that's happening here, and people wanted to figure out how to make the web better. So HTTP NG was an activity started for this. And one of the more interesting pieces of this that's most relevant to us is this thing called MUX. MUX was basically because session management protocol. Now, in the IETF, session is a bad word, and you don't say session protocols, or session layers are basically been banished from the TCP IP stack forever, except we keep recreating them in other forms. But MUX was supposed to be effectively what we might call today a transport or a session protocol, call it whatever you want. The idea was that it had many different things that they wanted to build under the next generation HTTP. What were these things? Reduce handshake latency, increase parallelism so that you can have multiple objects go over the same connection and not sort of get in each other's way. Provide an ability for the endpoints to schedule different objects within this connection. Allow for request cancellation. So if you at some point if you're serving a response and you want to stop serving that response, you should be able to stop that without having to terminate the entire connection. And finally, don't have many congestion controllers, because by then it was already recognized that multiple connections were a problem and they were going between the same two endpoints. So we want to coordinate that. We want to have all of those controllers work together. All looks lovely, but didn't really happen at the time, probably because the industry collapsed. I don't quite know this piece of history as to why this didn't happen. Most likely because most companies were not doing very well in the 2000-2001 period, many internet-based companies. And that's probably one of the things that happened for sure. So the goals for MUX were to multiplex many lightweight HTTP transactions onto the same underlying transport connection and deploy smart output buffer management, or schedule multiple objects effectively, or what we might today call streams on top of within the same connection. That was the big goal. So what happened while this is happening in the web world? Right? What's happening on the transport side? The stuff people wanted to build MUX, but what else was happening around the transport side? I'm going to go back to time in '94 when TTCP was happening. And this is basically some of you might remember this was built to effectively eliminate the TCP handshake latency. This was trying to make TCP lower latency for transactional use. DNS, for example, if you simply have a request and one response, it's supposed to be one round trip. But if I have to spend one whole round trip to do the handshake, I've increased my latency by 100%. So TTCP was supposed to be for that. It didn't get off the ground. It actually was implemented in many places. But one of the big reasons it didn't really take off was because it had some security flaws in that you could easily impersonate somebody and execute remote commands, because there's basically no authentication. There's no security for this. This is entirely done in TCP. And so there's no client address validation or anything that would happen before the server would operate on the application data. But that was TTCP. Starting in 94, the idea still remained. People wanted this. As you'll see, we'll come back to this. TCP session was Venkat Padmanabhan's PhD thesis, which I actually enjoy because I enjoy going back to this again and again. I won't get into the details here, but this one tried to separate TCP's service abstractions from congestion control and loss recovery. Now I talk about these as basically the top part of a transport and the bottom part of a transport. The top part is what applications want to use, service abstraction. And the bottom part is basically dealing with the network, recovering from loss, doing congestion control, doing stuff like that. And so this one allowed you to do multiple byte streams while combining the bottom part. And that's really what if you remember, what Marx was talking about. Similarly, congestion manager, if you remember again, 1998, this basically does similar stuff. It integrates congestion management across a number of applications and transports without regard to what exactly those applications might be doing. These are, again, in the same line of thinking. SCTP comes about in 2000 as an IETF protocol built for telephony networks, but it has a lot of these features. So there was a lot of excitement about trying to use SCTP for the web, for HTTP. And then work kind of stalled. There are a lot of you here, so I can't really make this terribly interactive, but at this point I would ask you, what do you think happened in this time? Maybe Robin, I can ask you, what do you think happened in this time? Putting you on the spot here.
I wrote in my thesis yesterday that nothing at all happened. It was silent until the speedy work started. Silence
happened. Well, so a lot of, actually, I was involved at some point in trying to get SCTP off the ground here. And I can tell you one of the big pain points that happened here, but I'm not going to go into it yet. Hang on. Well, so yes. So my pain points aside, one of the big things that happened was this is the time when the network had started to change. One of the big things that started to permeate the network were these things which organically popped up to serve different goals, but they were widely deployed in the network. Right? NATs, firewalls, protocol accelerators, various things that are getting deployed in the network, and they started to become the choke for what we could deploy because they didn't understand new transport protocols. Why does that matter? Because they actually stomped on transport headers. They needed to understand transport headers to do what they were doing. And because they couldn't understand new transports, they didn't let new transports through oftentimes. So we just couldn't deploy a new protocol at all. That wasn't the only reason, but that was one of the biggest reasons for the deployment of SCTP not happening. But it wasn't just SCTP. This was sort of a death knell in a lot of ways. These boxes, which we modify various transport fields, or at least read them at a minimum, and do various things with transport headers, were collectively called middle boxes. This is a term that Li Zhang coined, and I think it's a fantastic word. And it's basically something that we hadn't thought about as a part of the internet architecture, but they organically sprung up. And as I point out, well, these middle boxes basically perform functions other than what a router does, and it's on path. So it's not a router, it's not an endpoint, therefore it's a middle box. And these have now become what I call accidental architectural control points of the internet. Because we can't deploy new things without really getting around these boxes. So at that point, there's some other academic work. There's SST and Minion that came about around that time, and those basically recognize middle boxes in the network because SST was UDP based and Minion was all about getting through middle boxes. This stuff is remained academic for the most part. Some deployment happened of Minion, but it was sort of limited, and this was there. The IETF in the meanwhile standardized TCP fast open, which was reworking of TTCP effectively, or a retake on TTCP with some, because there was a need now again to do something exactly similar to kill the handshake latency. And MPTCP, which some of you may have heard about or seen earlier today at the other tutorial. All of these, again, TCP fast open, MPTCP was still trying to play nice with the network, in that they were trying to not assume a lot out of what mailboxes might allow, but they were still changing the protocol visible on the wire. How does that work? We already have experience. So this was a fairly bold strategy. And I would argue that the jury is still out there in terms of how successful these are going to be in the long term. So that's a tact that has been taken, but yeah, we'll see.
Don't
in the
tell
meanwhile,
Olivier.
HTTP-NG. What's it?
I said, don't tell Olivier.
Yes, we will have that conversation. So HTTP-NG happens. There's a long pause again because nothing's happening there, but eventually Speedy happens. And most of you might be familiar with Speedy. Not going to go into the details here, but at a high level, Speedy provides streams, multiplexing, flow control priorities. Again, similar things to what we talked about with HTTP-NG stuff. And this sits under HTTP. And this is great. This actually took off. This got deployed. And it got deployed as HTTP2. This became standardized. It's now traffic is actually increasingly moving to HTTP2. I don't remember. I don't have numbers off the top of my head right now, but this is what I would consider successful. But this is the stack that we have now, right? HTTP2 over all of these things. But there's persisting issues. We still have latency built into the network, and that is money. Latency is effectively money in today's date for a lot of services. And everything's going over HTTP. Video is going over HTTP. DNS is hoping to go over HTTP with DO. So HTTP needs to scale. If it's going to become a substrate for the future, it needs to scale. And it is already being used as a substrate. It needs to scale laterally so that there's a wider API, but it also needs to scale vertically in that there can't be any delays and inefficiencies built into the HTTP stack because things need to build on top of it. So you might be familiar with this trope, not this trope, this particular song. This is where I would play the song if I had more time. Every millisecond is sacred, but I'm going to move on and simply ask the question, how do we eliminate these inefficiencies in the web stack? We want to eliminate inefficiencies in TCP, in TLS, in HTTP, but also in the combined layering of all of this. And that's where QUIC comes in. So QUIC comes in to say, well, this is a stack that we love and we want to deploy widely. We want to eliminate latencies, inefficiencies, various things. We want to make it extensible for the future so that middle boxes don't stomp on this and don't allow us to extend this any further. And the Google QUIC experiment basically replaced that entire shebang, like the whole 3 layers, with a new crypto library, a new handshake, everything. And GQuick basically replaced the whole thing. This was, as I said earlier, a great experiment, and it was very successful. And when it came to the IETF, what we did was modularize it. And we now have TLS 1.3 that offers the same benefits as QUIC Crypto did. And so we can replace that with the more standard TLS 1.3. And HTTP 3 was designed to run on top of the transport part of this, which we now call QUIC. So that is the stack that we are working on today. That is the stack that we are looking at deployment numbers for. That is the stack that will be deployed. And these are various IETF drafts that if you care, you can go look up and look into. Why does the industry care about this? It improves site performance. That's the first thing. But more importantly, it also offers us control and agility. People might imagine that in the industry, the servers, we have control over the kernel, control over everything else. But the main thing to remember here is that transport is basically living in the kernel. TCP is living in the same address space as super critical functionality that a server needs to handle. Device drivers run in the same address space as the transport does, which is insane because the transport is not that critical. You can put it somewhere else. And if a connection dies because the transport instance crashes, that's perfectly fine. The system doesn't have to crash. So bringing a user-space transport makes it possible for us to have tremendously higher agility and iterability in transport deployment. It enables other architecture exploration because we can make these changes much more easily up in user space. And we can deploy new features now on the network. And that's the promise of QUIC going into the future, is that now, because we are creating this encrypted path that can't effectively, and we'll see later, it can still be ossified, but doesn't get ossified easily. We are trying to create a space for the future. What I'm going to do is, well, I go just very quickly. lot of implementations in progress, specifications are in progress. Hopefully, we are hoping to have the RFCs done in next year, but that shouldn't be your thing you're looking at. What you should be looking at is where implementations and deployments are, and those are happening. So later this year, we expect to see a lot more IETF QUIC traffic than we see now, even before the RFCs are published. And that's where we are right now. That's the end of my first section. I'm sorry I ran 2 minutes over, but let's just take 2 minutes break and we'll come back and continue on with the next section. I'm going to play my music now. Wait. If I can find. I'm not going to play my music. I can't find things in Switch rapidly enough. All right, it is 3 minutes past. I am going to start up again. Welcome back. We will continue with discussion of basically now we'll start jumping into some of the details of QUIC. And again, this is going to be a little bit of a, there'll be some detail, but I'm going to have to not get into the lot of details. This is really hard to get a lot of details within such a short period of time. For a protocol of this complexity, but I will try. So my goal here is to get you to understand how the QUIC handshake broadly works, what QUIC headers look like. I will talk about connection migration, some of the issues that have to do with connection migration, and then I will toss it over to Robin, who will actually show you QUIC packets using Wireshark and walk you through how you might use Wireshark to look at QUIC traces. Let's get going. So, hang on, there we go. So why QUIC? Why should somebody use QUIC today? The heritage of this aside, if somebody was to ask you why is QUIC important, there are three broad reasons why. low latency, encrypted transport, and resilient connections. I'll talk about each one of them in turn. The first one, what does low latency mean? QUIC eliminates the latency of new connections to recently visited sites. This is again in the line of, as I said earlier, TTCP and various things, but we actually make this happen. The new connections should experience what we call zero RTT, handshake latency, meaning that the client should be able to send traffic along with a handshake packet instead of waiting for a response from the server before sending a data packet. It also eliminates head-of-line blocking that is prevalent in TLS and TCP because TCP is a byte stream, and putting multiple objects over a byte stream causes head-of-line blocking there. The handshake, I'll walk through the handshake in a bit of an overview, sort of a high-level schematic sense. Here's a TCP and TLS 1.3, specifically 1.3 handshake. Remember that TLS 1.3 already cuts back latency from TLS 1.2. I should have checked. You can hear me, right? Yes. We're a little bit late to check that. But you got the SYN-SYN-ACK handshake of TCP, followed by the TLS handshake that does the client hello and the response from the server. And then you get to do the request and response. That's TCP with TLS 1.3. And that's on the first connection to the server when TLS talks to a client. So there's two handshakes, two round trips of latency before data can go out. With QUIC, on the first connection to the server, you have an initial packet that carries the client hello, as well as an initial packet coming back that carries the server hello. And then you get to send data. You might notice here immediately that in TCP, you can see the layering of the protocols. First, the TCP connection happens, SYN-SYN-ACK, and then TLS connection happens, hello, hello. In QUIC, we've compressed that. So the QUIC and the TLS handshakes happen together in the same packet. And that's one of the bits of magic that we weave here, is compressing those in. Even though it is TLS 1.3, it's now weaved in with the QUIC handshake. And then immediately after that, you can get your data flowing. So we save that one RTT right off the bat. On subsequent connections to the server, with TLS 1.3, you get the zero RTT that TLS 1.3 offers, but you still have to pay the penalty of doing the SYN-SYN-ACK for the TCP handshake. And then you get to send the hello, but along with the hello, you get to send data with the zero RTT in TLS 1.3. With QUIC, again, because we've combined the TLS 1.3 and transport handshakes together, you get to send everything in the first round trip. The transport handshake, the TLS handshake, and the data. It all goes out at the same exact moment in time in the same packets. So that's low latency handshake. The QUIC handshake itself. So in here, I said there's an initial packet. I won't go to the TLS 1.3 handshake. That's not the topic of this thing, but the QUIC handshake part of those packets carries a few things. It carries flow control, basically initial settings, as you would imagine, negotiations, initial settings, things like that. And it packs them in these things we call transport parameters. And those transport parameters are, this is some of the magic we weave, like I said, sent to TLS as an extension. So we tell TLS, here's all of the stuff that I want you to pack into your handshake that you're doing there. And TLS will pack it and figure out how to send it, but it gets packetized as QUIC. TLS then turns around and tells QUIC, hey, here's my message. And then QUIC says, okay, I'm going to throw it in one of my packets and send it along. So QUIC and TLS have a very interesting dance here, and we had to do a lot of work on the API between QUIC and TLS to make this actually reasonable and meaningful. But it's a very different architecture here than your standard layered architecture. So during the handshake, you also exchange connection IDs. The two endpoints exchange connection IDs. Each endpoint says, I would like you to use this connection ID when you're trying to reach me. Why does every endpoint choose a connection ID for packets that are coming towards it? Because connection IDs are effectively used for routing within the server infrastructure. So these are in the QUIC header. They really shouldn't be used anywhere else in the network. But the server infrastructure goes, oh, this is the connection ID. I know where to send this packet, which server to send this packet to. And so every endpoint knows whether it needs a connection ID for packets coming to it or not. And so it can choose the length. It can choose the length to be 0 if it wants. If you're a client, you're typically going to say, I don't need a connection ID because I don't have any connection ID based demultiplexers sitting in front of me. So make the connection ID length 0. The 4 tuple, the UDP ports and the IP addresses are adequate for demultiplexing to me. Now, one key thing here is that the connection IDs help you do is because if routing happens on connection ID, that means you can change the 4 tuple. We'll get back into that in a moment. So the TLS handshake, like I said already, is carried in QUIC packets. Even though QUIC hands its transport parameters to TLS, TLS hands the messages back to QUIC, and QUIC packetizes and ships them as QUIC packets. Again, this is a detail. If you didn't track that, that's fine. But this is one of the interesting bits about TLS and QUIC interactions. Ultimately, what flows on the wire is all QUIC packets, as Robin will show you later. The reason we do all of this dance is so that we can protect the QUIC handshake itself. The QUIC handshake goes as TLS options. So all of the QUIC transfer parameters are effectively protected by TLS in those TLS extensions. Encrypted transport, they are fundamental. Encryption and privacy are fundamental to QUIC. They've been part of the design right from the get-go. They protect the connections from tamper and disruption. Most of the headers, we've designed it so that they're not even visible to third parties. Now, this didn't come at no cost. And many people who are on, so there are several people on this call who have been burned by this point. This is understandably a point of contention because the network can't see anything about the transport. But why did we do this? I'll talk about why we did this in a second, but I'll show you what I mean by this. So this is the packet header with HTTP using TLS and TCP. You got the TCP header there, and then you've got the application data, which is HTTP headers and payload. And with TLS, really, you protect this part of it, right? The part in dark is completely invisible. The part in gray there is visible. That's the TLS headers, but it's visible, but you can't. It's tamper-proof. You can't change that. The rest of it, the transport TCP headers, are completely open, visible, and modifiable in the network by third parties. So what can you do with this? Well, as it turns out, you can do a fair bit. This information, this metadata is not, it can be used for, so there's this paper a few years ago, 3 years ago, which shows that you can identify which video somebody is watching just from looking at TCP headers. And it should become immediately obvious if you understand that this is the compression, the sizes basically of packets, and are effectively become signatures here. Now again, in QUIC, you can actually pad and pack against this and make this invisible. These timing signatures, you can hide these timing signatures. But this is the sort of stuff that can be built and deployed. There you can look at a TCP connection, just looking at the TCP headers, you can predict, you can detect the video that's being watched in this case. So our maxim in designing QUIC was this one. It's an old one, but a good one. That the ultimate defense of the end-to-end mode is end-to-end encryption. So whatever we want to protect, whatever we want to retain control of between the endpoints, we don't simply put it out there and tell the network to play nice. We protect it by encrypting it. So what does an HTTP with QUIC packet look like? It's like this. That's the UDP header that you're seeing up there, the port and port length and checksum. Below that is the QUIC header, followed by HTTP headers and payload. And with encryption, that's what it looks like. You basically encrypt everything, and there are a few bits which we need. And there's actually 1 bit in there. There's a whole draft right now for not basically encrypting that 1 bit, not quite encrypting, but greasing that 1 bit up there, the second bit up there. And that's what we got. The destination connection ID is visible as well in the network, and I'll talk a little bit more about that in a moment. So that's what's visible. So we protect basically all of the TCP headers, including, as you might notice, the packet numbers. That's important, and I'll get to that in a second. So your sequence number in TCP is no longer visible in QUIC. We call it packet number in QUIC. And QUIC gives you resilient connections. It gives you connection migration. It gives you improved loss recovery. And Ian will talk much more in detail about how loss recovery improves things with QUIC over TCP. But I will talk now briefly about how connection migration solves things. So connection migration is basically something that Apple has used MPTCP for. You may have heard of that for solving the parking lot problem. Again, if you were in the session this morning, you might have a little more clue about this. But we use connection IDs, 18-byte connection IDs that are part of the QUIC header for doing connection migration. Basically, here's what it looks like. You're sitting at home on Wi-Fi, connecting to a server, and as you move over to the cellular network, move out of the home, your connection goes with you. Now, of course, as a client, your port table changed. You rebound you connected to a different network now, so your IP address and your port number on the client side have changed, and the server has to be notified of the change, or has to still be able to pull data that's coming from you from a different IP address and plug into the same connection. That's where the connection IDs are helpful. So what happens here? When I'm sending packets to the server, I'm using, let's say the destination connection ID I'm using on all the packets is this one, is this EDC destination connection ID. What the server does while I'm doing that, now bear in mind that if I was to do this, one of the problems, if I was to simply move and my connection ID was visible to the server and the server could tie it together, then it would be wonderful. But if my connection ID, as I showed you, is visible on the network, which means anybody, any third party that could observe this could correlate me moving between these networks. And that's a privacy leak if we wanted to protect against that. So anyway, so here's what happens. The destination connection ID is set to this value. And during the connection, under crypto cover, under encryption, the server sends me a bunch of what are called new connection IDs. It says, hey, by the way, you can also use these connection IDs to reach me, and I will believe that you're on the same connection. And the server sends these. Why does the server send these? Because the server knows how to generate new connection IDs that will make sure that those connections still come back to the same device and it can be demuxed to the same connection. And the client now has a stash of connection IDs to use. They were sent under encryption, so nobody in the network could have observed them. So when it moves to a new network, the client starts to use a different connection ID. So a third-party observer can't correlate the connection moving between these two networks trivially anyways. I mean, this is not to say that you can't correlate, you can, but this is to avoid trivial ways of correlating. So in addition to this, if the packet number were visible, the packet number could have been used as a trivial way of correlating across this connection moving across networks. And we handle that with packet number encryption. But there's a fundamental issue in packet number encryption. I'll talk about that now. The packet number is basically used as a nonce for packet encryption. So your whole packet is encrypted, and and encryption needs a nonce, which is basically a value that's only used once during the entire connection, or during the entire crypto context at any rate. And so you can't repeat the packet number. The receiver needs it to decrypt the packet, however. So you need the packet number to be visible to the receiver so the receiver can pull it and then decrypt the entire packet. And we make it monotonically increasing also for loss detection and for compression reasons. And Ian will talk more about how it's useful for loss detection. So this is what a packet number is used for right now. And that's how it's used for in QUIC. But if you were to encrypt this, the receiver wouldn't have it. And furthermore, well, as I pointed out, this is one way in which you can correlate. In addition, visible bits tend to get ossified in the network because metal boxes build behavior around that. Oh, hang on a second. In addition, so if you want to encrypt this, you would also need another nonce because encryption requires a nonce. If we want to encrypt the packet number was the nonce. So we don't have another nonce. And so we had this problem. So we weren't encrypting packet number for a while until a colleague of ours, Kazuo, came up with this, and well, others in the working group as well. But there was a really nice insight that once you encrypt the packet, the bytes in the packet are effectively random. And we can basically sample those bytes to make that a nonce. And that was the idea that allows us to do packet number encryption. Of course, this is not super strong encryption, but it's enough for packet number. So that's what we do. For every QUIC packet basically goes through packet encryption and a packet number encryption phase. So there's two step encryption here that is done for QUIC packets. So if you didn't follow all of that, that's perfectly fine. This is described to some extent in the draft, but there's also other posts I can point you to if you want to understand this. So as I want to basically just walk you into a couple of things. I'm not going to go over this one. I'm going to skip these right now, but just say that the top and bottom parts, as I pointed out earlier, to any transport. The top part is application-facing functions, and the bottom is network-facing functions. And in our case, right now, these are sort of the top and the bottom parts of the transport. And there's also encryption, decryption, and handshake that happens over the entire thing. Of course, in the case of QUIC, almost all of this is encrypted and not visible on the wire, as I pointed out earlier. I'm going to show you a few packet headers, and that'll be the end of this section. We'll move to actually looking at those real packets in the network. But broadly, QUIC packets show up in two different types. There's a long header packet and the short header packet. The long header is used almost, it's not required to be used only for, but it's almost always only used for the handshake alone. This carries a lot of things like version, like negotiation of the connection IDs happen here. And these are things that some of these things are not required afterwards. Like, for example, if I'm establishing a connection with somebody, I'm saying, okay, I speak this version, you speak this version. But once you establish that connection, I don't need to keep sending you the version. So this is used right now to establish a connection with somebody you're not spoken with, or you're trying to establish a connection with. Once that's done, there are 4 types of long header packets: initial, zero RTD, handshake, and retry. And all of these are basically used during the connection setup phase of QUIC. And then there's the short header packets. And if you see, the short header packets basically doesn't need all of those other bits that we were using for long header packets, because once a connection is established, I can simply use the destination connection ID and the port IP tuple to get packets to the destination. And I don't have to negotiate all these other things. So I'm not going to keep sending version, for example. I don't need to keep sending that once I've established the connection. So those are the 2 types of headers. And that's where I'm going to stop. We'll do a 2-minute break again and come back, and we'll actually look at these in Wireshark with Robin. I will point out, I know I've been just going and going and going. It's a little strange to do this over Zoom with so many attendees, because I like to keep things interactive, and it's really hard to do that right now over this call. And it's also, this part of it was a little slide heavy and just sort of talk heavy, but I think we are at the end of that sort of a thing. It's going to be more interactive and more doing things.
Does anyone have any questions or kind of just...
But anyways, we've tried to keep it a balance.
Right. Can I ask something quick?
Certainly.
Right. Is it possible to, like, in a demo, to show connection migration part? That sounds very interesting. If it's possible, like changing the connection between 2 and still.
It is possible. I don't think we have one immediately available, unless maybe Robin does. I don't know.
Okay, no problem.
There are.
I was walking through who all is here. Everybody's got their videos off.
Okay. Yeah, there are multiple stacks that do migration, but yeah.
I see Lucas here. I should shout out to Lucas Purdue, who is from Cloudflare, and he is one of the chairs of the QUIC working group at the IETF. So if you don't like things that you're seeing on these slides, you can blame him.
Hi, my audio is awful, so I'm on mute. But yeah, behind me, if you can see my video, I didn't realize, I forgot, but the virtual background is actually the QUIC BOF from IETF 96, I think. So yeah, good old times.
Oh my God, Lucas, you are like an IETF ghost.
For the record, that's IETF 96, not 1996, because even though the QUIC working group has been going on for a long time, it's not quite that long.
Oh my God, that's right.
Jana, could you allow me to share my screen?
Oh yes, sorry. Let me stop sharing. There you go. You got the floor, Robin.
Yes. Should I just start or?
Yeah, get started. I think it's time.
That's great. So as you can see here, there are several ways that we will look at how to actually debug QUIC in practice and how to look what it's actually doing in the network. This is the first of two main demos with Wireshark because we think most people already know this tool and it should be easy to understand. So you can follow along at home, as I said, on the Slack, but you need an updated version. And most of the rest of this is mainly for if you come back to these slides later. I want to explore this a little bit more. So let me just jump right in. If you are following along, then you should have found the PCAPs in the 0_Wireshark folder. If you just double click on the PCAP, that should open up the Wireshark. Or if you have two different Wireshark versions, you should manually load it in the correct one, of course. And you should see something like this, very similar to what you used to from TCP, but now, of course, the protocol column should say QUIC, obviously. So let's look at what we can see here. At the top, like Jana said, we see a couple of different types of packets. So here, the first column here is you've got initial packets, handshake packets. And then we have protected payload packets, which are the 1RGT packets. There's a fourth type for 0RGT, but that is not included in this trace. But you can also, of course, do that in Wireshark. So we can see here is already a little bit weird because we see three initial packets instead of just one. And if we look at the time indicators on the left, you can actually see that the two follow-ups were actually sent 200 milliseconds after the first, which means that the first was deemed lost, and the client actually retransmitted the first initial twice to make sure one of them got through to the server. So that's basically what you see here. And let's click open this, because as you see, IETF is backed into UDP. But if you open this up, then we're going to start to see what Jana was talking about, because Jana, of course, doesn't lie, that in the QUIC initial packet is indeed a TLS. And this is pure TLS. It's packed inside what they call a QUIC crypto frame, which we'll discuss in a moment. But within there is just a normal TLS 1.3 client hello message, basically. And so this looks exactly the same as what you would get if you opened up a TCP TLS 1.3 packet. With of course, the main exception being here that here is an extra extension in the client hello, which is called the QUIC transport parameters. That I think Ian is also going to discuss a bit more later on. But basically, this includes kind of the transport settings that you want your connection to have. And there are several of those. I'm not going to discuss all of them in detail. The ones I did wanted to highlight are the first 6 ones, which are all called max stream or max data. And these are all to do with QUIC's flow control features that I'll discuss a little bit after this as well. So that's basically the way that the client initiates the connection with the server. I'm just going to look at here. Okay, yeah. So we can see that there are actually 2 QUIC packets inside of this initial packet. The first one is an actual, there are 2 QUIC packets in the initial datagram. First one is the initial packet, and the second is basically just padded. Because for security reasons, QUIC expects all of the initial packets to be padded to their full length, which I think is 1,280 bytes at minimum over QUIC. So that's what you will see. You will see these are in this case 1282 bytes in size. So finally, one of the second 2 got through to the server, and the server sends back a handshake packet. Now this is a bit strange to see in Wireshark, because this is actually both an initial and a handshake, as you can see here as well. So the top one is actually the initial packet that server sends, as you can see here, which includes the TLS 1.3 server hello message. This one is still sent unencrypted, so you can still see what's included here. Interesting to know here is that this one does not include the quick transport parameters that the server sends. Those are not sent in the clear, those are actually sent encrypted in the handshake packet, which is beneath here. And now, this is basically what Jana was also trying to say, and that we clearly see here. We can't actually see into what's happening in this handshake packet, but because from this moment on, the full QUIC connection is actually completely encrypted. There's no way that we can look inside of the packets anymore. With this whole handshake thing, we can still see the fields in the headers, because this is the long header format. So you can still see things like the connection IDs and the version, all the bits, but you can no longer see in the contents. And this only gets worse with the last type of packet that we have here, which is the actual 1RTT protected packets. Which is this one, and this is a short header. As you can see, a short header packet. And basically here, we have almost nothing, right? We only have a couple bits, and there should also be the connection ID here. But Wireshark is hiding it because you can already also see this in the handshake packet first. You can't see those here, right? Here you can see the connection ID being listed in the short header packets as well. So basically, this is what you get from loading an encrypted quick trace into Wireshark. It's interesting, but especially if you start scrolling down, it's not all that useful anymore, because all of these things are simply completely encrypted, and that's not all that useful. Let me see if I didn't miss anything. Yeah. So this is, again, done for very good reasons. However, this has some downsides as well. So if you want to actually use this for debugging or analysis of what's happening in the network, you're going to first have to decrypt it, which is what we're going to do in a minute. But let's think about how that happens in practice if you do this on a production level network. They would basically have to store the entire encrypted packet capture to disk to then post hoc decrypt it and see what was actually going on. This full packet capture can be quite large, because of course it contains all of the data, not just the quick transport metadata. So for TCP, what you can do is basically just capture, like, say, the first 100 bytes of each packet and only store that, and then look at that live, because all of that is in the open. You can't do that with QUIC. And that leads to some scalability issues that I will come back to afterwards when we discuss logging formats for QUIC. So first, let's look at what this looks like if you actually are able to decrypt it. So there's a second file together with the PCAP. It's called the keys file. And to get that into Wireshark, that's actually quite involved. So if you're following along at home, try to keep up. You go to Edit on the top. Then you choose Preferences. That's all the way on the bottom. And when you have that on the left side, you should see one of the items says Protocols. You can click it open, and then you have a huge list of protocols. And you just scroll down to where it says TLS. Or I have a nice trick: if you just click on one and then just type TLS on the keyboard, then it will actually jump to TLS as well. And then in the TLS preferences, there is one very interesting field here, which is called the pre-master secret log file name, which basically means that you just need to put there the keys file that I delivered to you. These contain the encryption keys used by TLS that you can extract from most of the QUIC stacks using the SSL keylog environment variable. More details are in the slides. How you can practically do that. So basically, you can get these keys, and if you load these keys into Wireshark this way, you'll see that suddenly things change. Now, all of a sudden, we see a lot more information here next to all of these packets. And if we open up one of these short header packets now, you can actually see, oh, we suddenly do know what the packet number is. We also know that there are some new things which are called frames that we're seeing happening inside of the packets, which is, of course, what you expect because you now decrypted it. So let's look at a couple of interesting points that are not always as clear to new people. One of the things is that QUIC does not use sequence numbers like TCP. It uses packet numbers, which is a bit more, I think, at least logical and easier to follow. But one of the things that you will see here on the top is that those packet numbers aren't unique. So we start with a 0, 1, 2. And then you have, I need to make sure here, Here is another 0 basically being sent from the client. These are from the client, another from the client. So some people find that a bit strange. That is because the packet numbers are always monotomically increasing, but only within what they call a single packet number space. Jana mentioned that before as well. So for each of the types of packets for QUIC, you have a new resetting packet number space, at least in most of the implementations. Some of them don't do that, and they just keep on going up, but some do. So that's something to keep in mind if you're looking at this for the first time. These packet numbers might reset or look to reset, but that's actually normal across the different packet number spaces. That's one of the things. Another thing, maybe alluding to the question that was asked just now, looking at a bit more the connection migration things. So this is what you see here, the NCI things happening here at the top. Those are actually the new connection ID frames, as you can see here. That's what John also talked about. The server is now sending a couple of potential connection IDs that the client can start using for when they start migrating to a new connection. However, they don't have to wait for the migration to happen to start using these connection IDs. They can actually use them right after the handshake completes. And that's basically what you see happening in this trace here as well. So in this trace, let me see. So here we had these connection IDs, the 1278, and that switched to CD5, ED, whatever. If we look at, excuse me, if you look at these things in here. So that's another thing that you might see, and that's another thing that makes it a bit more difficult to analyze QUIC without proper tooling, is because you can have a single connection, changing connection IDs for that same connection, even though it's not switching or migrating or anything, jumping around, and the only thing that you have to link up these connections is this connection ID, right? Because it's the only thing that's visible in the encrypted short header packet, which is great for privacy and it's terrible for actual debuggability, right? So you need to be able to decrypt this to view the new connection ID frames inside to know which connection actually maps to the same physical or underlying connection conceptually, which is something we and others have been bitten by before. So I thought I'd just give you a heads up. So let's look at what else can we find in these packets. So I said before that we also have crypto packets. Predictably, these contain cryptographic data. So QUIC integrates TLS 1.3, but it's not like it's a super tight integration. The idea is that you should be able to swap out TLS 1.3 for something else later on. And so all the encryption handshake stuff is encoded in these crypto frames. And QUIC doesn't really look inside them. So you can easily swap that out by transporting something else in these crypto frames in practice. What else do we have? We have ACK packets, ACK frames. So acknowledgements in TCP are sent in the header. In QUIC, they are not. They are sent in separate frames as well, because not every packet needs to contain an acknowledgement, and so that saves a couple of bytes over time. Now, let me see which one do it. Packet number 62 was interesting. Okay, so QUIC's packets, QUIC's acknowledgement frame format is quite involved. It doesn't just list the packets that were acknowledged or that were lost. It's kind of a complex incremental compression scheme to say just save another few bytes. I think Jana's going to explain a bit more about that soon. But so you can see here that it's like a couple of ranges and gaps between the ranges and all that. And it's kind of difficult to figure out, I think, from this kind of list, which packets were exactly deemed lost by this acknowledgement or not. Which of course we'll see some solutions to soon. Let me scroll through here and see if we can find something else. Here we have a ping frame, which is also embedded in the QUIC, which is used in some settings to try to elicit a response from the other side or to pad a packet a little bit. Let me see if I can find a MSD. Yes, here. So here we see on the top right, we have an MSD. And what does that mean? It's a max stream data frame, which is part of the QUIC's flow control setup, which we'll also see later how exactly that works. But so you can see that unlike TCP, which indeed uses headers, which I think Kanta explained very well during the multipath tutorial just now with his ship analogy, and that QUIC is like a container ship shipping different containers, and each frame is a container. So I think that shows us nicely. Instead of having a single receive window in the header, we actually have separate individual frames in the QUIC packets that carry the same type of data at least. Now, the final thing that I haven't talked about, but that is by far the most ubiquitous type of frame that you can see here, is the stream frame, right? Almost every packet has a stream frame. And that's because, of course, the stream frame is like the main data carrying amenity that QUIC has. This is basically where all the data from the upper layers is going to be found in. So in practice, the HTTP3 data is only going to be found in QUIC's stream frames. Or if you're doing DNS over QUIC, you will also see the DNS frames, the DNS data there. The thing here, Wireshark currently does not fully support HTTP3 yet. It has, I think, a little bit of support. Let me see here. So these are the initial steps for the client requesting something from the server. And if you look at here, you can see that it is semi-readable plain text HTTP request, which you normally shouldn't have because HTTP3 does header compression with the QUIC algorithm, so it should be opaque. But apparently Wireshark still does a little bit of figuring out what it should be already. But for most of the other things, it doesn't really have much support for HTTP3 yet. You can see this here. Normally what you expect here is to see that in the stream frame, there would be an HTTP3 data frame, or in this case, a headers frame, HTTP3 headers frame containing this request, basically. Now this is, it's not in Wireshark yet because it's just really difficult to implement because you need to keep track of lost data in these streams. You need to reassemble the individual streams before you can actually do the HTTP3 dissection. But they're working on it. I think the plan is to have something within this month or maybe next. So it's definitely coming. But for now, don't be surprised if you don't see HTTP3 frames showing up inside of Wireshark yet. That was kind of all of it for me. With 1 more minute to go, so I think we can shut this down early. I think the idea is to have a 2-minute break now, right? And then we'll continue. Thank you.
Yeah, let's do a 2-minute break. All right, Robin, shall I share this? Can you stop sharing so I can share?
I'm going to do the next 2 slides, right?
Oh, sorry. Yes, you're right. Yep.
And then I'll immediately shut down.
Yep. No, I can pull it from you too, so don't worry. All right, let's get started then.
All right. So don't worry, you're just stuck with me for 2 more slides, and then I'll pass back to Jana. What we're going to look at now is a bit more in depth about what these streams and the flow control and the different frames are actually all about. Because you might have like an intuition for it, but let's look at a bit more in depth. The first thing that I'm going to talk about is QUIC streams. Like I said before, these stream frames are basically what the data is being transported in. And the nice thing about QUIC is that it has the ability to create these streams at will. The stream is basically just a new stream ID. And the stream ID is like a 26-bit field, so you can have a lot of different streams going on. It's very, like it says here, lightweight. You can very easily start a new stream. You can also very easily abort or reset a stream or abandon it without too much problem. I think at one point there was even a proposal to send only a single packet on individual streams so that you would never be head of line blocked on the stream again. I think that was for the datagram proposal. So yes, streams are very easy to make, and you will see a lot of implementations using a lot of them easily. So each of these streams, to me, the way I always interpret it is each individual stream is basically like a full TCP connection, at least when it comes to having a byte stream abstraction that takes into account the ordering of the bytes and how they are retransmitted in turn. So you can have multiple concurrent streams, parallel streams happening at the same connection at the same time. You could also do that with TCP if you used HTTP2. But then you would have to, the problem was that TCP does not understand that there are multiple different streams. So it still sees everything as one big stream. And if there's one packet lost in this entire stream, you will have to block everything behind it, right? That's the eponymous head of line blocking problem. And this is, for me, like one of the main things that QUIC solves. The main difference between QUIC and TCP is that QUIC removes this head of line blocking problem, at least between different streams, because now the streams are fully independent. So tracking which data was lost and how it is acknowledged is done on a per stream basis, not on a per packet basis. Which means that it should help for performance. We will see a little bit later that might not always be the case, but it's an interesting concept nonetheless. The thing is that because you now have these multiple independent streams, you still have just one underlying QUIC connection, right? You have only one congestion window that you need to fill. And let's say you need to fill 60 packets of the congestion window right now. Which of the streams are you actually going to send? How do you make that decision? That's what we call the streams need to be multiplexed onto the individual connection. And there are an extreme amount of different ways of doing this multiplexing, which is basically what a lot of my work in my PhD has been about. As you can see here, here you can see that each line basically is a different QUIC implementation on HTTP3 multiplexing scheme, and each of the colors, each color represents a different stream. So if the streams are still too abstract, you can see each stream is a different file on a web page, right? Stream 1 is the HTML, stream 2 is the JavaScript file, stream 3 is the CSS. So you can see just here from the high-level visualizations, it's clear that there are so many different ways in which you can do that, and that it becomes even worse because HTTP3 and HTTP2, they have prioritization systems that actually help you drive this behavior. This would take way too long to go into detail, so let's get back to streams themselves. In QUIC, you have basically, well, let's say 4 types of streams. These are not really all that different functionally. They're mainly in what you allow to happen. Do you allow a server to start a certain type of stream? For example, in HTTP3, the server cannot start bidirectional streams in which the client can also reply to with data, just because that's the way the protocol wants to work. So this is basically just a toolbox for application layer protocols to have a bit more control on the type of streams that peers can open within the connection. The final thing that is with streams now is with TCP, you have just a single flow control limit, which is the receive window, which is again in the TCP header. Now with QUIC, because these streams are brought into the transport layer, you suddenly don't just have one flow control limit, you have three, right? First, you have one for each individual stream. So you can shut down individual streams at will. You have one overarching connection control, flow control limit, which is basically the same as TCP. And then you also have a flow control limit that limits the amount of streams that you can open. So the individual count of the streams that you can open as well. And so it's very powerful, very flexible, but in practice quite difficult to get right. We did some tests recently that showed that almost all of the implementations use QUIC flow control very differently. And it's a big one because it can really impact your performance. So that's definitely something you should keep in mind if you start playing around with these things. With that, I'm going to pass it back to Jana, who's going to tell us more, or Jana can maybe just, who's going to tell us more about other frame types. Thank you.
Thank you, Robin. Can you see my screen? Okay, cool. So yeah, that's actually a great point about the flow control limits. This is always a difficult one to get right, and it's gotten a little more complex in QUIC. But again, as I tend to point out, you don't get all the benefits of QUIC for free. So you have to learn to manage some of this complexity, and it's manageable, but you have to be mindful and careful. What I want to do is basically walk you down. We left off at the packet headers. I want to show you a little bit more of what happens inside of packets, and when you are basically, if you have if you understand how things happen in TCP, you can compare and contrast. If you don't really know the details, that's perfectly fine. I'll just show you how things happen in QUIC anyways. So as I said, the long header earlier, and as you saw in the Wireshark, the long header is used mostly for the handshake, and the short header is used afterwards. Inside of either of these packets, both of these packets are simply containers, as Robin was pointing out earlier. They're simply containers, and what they contain are frames. A frame is a generic data structure. Think of it as that. And a frame has a frame type that gives you the type of frame it is. And then for every type, there are fields that can go in there. So a frame basically has a frame header that tells you the type and the fields that are in that particular frame. So this is all contained inside of a QUIC packet. Here are the list of frame types. I'm not going to go into all of them, don't worry. But there will be a test at the end of this, and I will ask you the frame ID, and Ian will have to answer that, and we'll all fail basically. But the ones that are interesting, you've encountered some of these already. You may or may not have noticed some of these, but there's the ACK frame and there's a crypto frame. The crypto frame carries the handshake stuff, the material that we're talking about, the TLS messages that gets carried in crypto frames in QUIC packets. The ACK is your beloved acknowledgement information in TCP. That's basically the one field, and the SAC options, but we'll talk about the ACKs in a moment here. And all data, application data, is carried in this one frame called a stream frame. So what are all of these other frames about? All of the other frames are basically control frames. In QUIC, all control information is in frames. Robin pointed out that flow control was through signaling, and that was basically your max data, max stream data, max streams, data blocked. All of these things are basically for things. There's a new connection ID. We talked about that. There's very other things, path challenge, path response, that are useful for connection migration. All of these are frames within QUIC. Okay, so let's look at a stream frame for an example. So here's a stream frame, has the stream ID. This is the stream frame type. I'm not talking about the type is there, but there's a stream ID. And then there's the offset within that stream. So a stream is effectively, as Robin said, it's a byte stream. It's a stream of bytes. It's supposed to give you that abstraction that people are used to with TCP. But in this case, that abstraction is available within a single stream. So there's a stream ID that just gives you an identifier for a stream. An offset as to which byte offset this data goes in that stream, the length of this particular frame, and then the data itself. So let's look at an example here of packetization, right? So here's a quick packet, the container, and then there's the header bits, and I'm not going to walk through each one of them, but there's a spin bit, the destination connection ID, and there are things that are encrypted, visible, but potentially encrypted, well, but encrypted. So in this case, those are the head. That's the packet header. We've seen the packet header, and then there are frames. So in this case, particular example, I have 2 stream frames and an ACK frame. In the first stream frame, so let's look at a more concrete one here. This is the first stream frame has a stream ID of 5. This is the 5th stream, has an offset of 1123, a length of 500 bytes, and fin is false, which means this is not the end of the stream. More data might flow. This frame at any rate is not closing the stream up. And then there's data that goes into the stream at offset 1123 of stream ID 5. This is now encapsulated, as you can see at the bottom left there, in packet number 56, random arbitrary packet number. Similarly, because I can do multiple streams here, I might have multiple streams open at the same time, I can pack another stream frame from another stream into the same quick packet. This is the stream multiplexing that we are able to do within a packet. As it turns out, this is not a great idea because this actually introduces head of line blocking. If you drop this packet, your 2 streams, 5 and 8, are both blocked. So it's not necessarily a great idea to packetize it this way, but as an example, this works well. So let's say that stream ID 8 has 300 bytes. And in this case also, it's not the end of the stream, and there's stream data in there. You can see that the offset field is missing from the second stream. That's not a typo. It implies, it's implicit. When the offset field is missing here, it just means it is starting at 0. So now we are looking at those things. Now the ACK frame is a little more convoluted, so we'll look at the ACK frame in a bit more detail here. I'm not going to walk into all of these details in depth, but I'm going to touch on all of them. So the first thing that it shows there is the largest acknowledged so far. This is the highest packet number seen so far. Now this is a major departure from TCP, by the way, because TCP shows you the cumulative ACK point. This is not the cumulative ACK point. This is simply the largest ACK we've seen so far. And the acknowledgement delay, the subsequent field, tells you how long has it been since I received the largest ACK to when I sent this ACK. Now, very simply put, this captures your delayed ACK delay. Let me finish this frame, Sahil, and then maybe I can let you in. So the delayed ACK information is actually packed in. Now, this is something that is not visible in TCP at all. A sender does not know how long the receiver delayed acknowledgements for. In this particular case, that is actually explicitly sent back in the ACK. And then there are ACK ranges, as Robin showed you, but basically these are simply ranges like SACK ranges, but contiguous from the largest ACK down. So the largest ACK, and then the range is going down from there. So that's roughly how it is. Sahil, do I need to unmute you for your question? I can't see you. Well, Ian, if you can find Sahil, maybe he can unmute. Feel free to interrupt me. I'll just keep going. So the ACK frame, this is what the ACK frame looks like. I know it's a lot of information here, but moving along, let's say in this particular case, I see Sahil. You have to unmute yourself.
Hi, I don't know. I don't have any questions. So.
Okay. Okay. You're
I guess it's from the. I don't know. I'm not able to. There is some bug.
That's all right.
Right. So I'm not able to.
That's okay. Just.
Right. Sorry. Yeah. Continue.
Not a problem. So basically here with the ACK, this is an example of an ACK packet, an ACK frame. Let's say at this point, the receiver has received packets 1 through 125. All of them have been received. And the time since the largest received, which is packet number 125, happens to be 25 milliseconds. We need to represent that as a shifted value. So this is to allow for this delay to scale. In QUIC, that is negotiated. The shift is negotiated, but it's negotiated and then thrown into the ACK frame. So what is thrown into the ACK frame is basically this value here. The the ACK fields here are basically the largest packet received so far. The delay, the particular representation doesn't matter so much, but just remember that we've had that delay in here. The ACK field, the largest packet received so far is 125, as you can see. The first ACK range tells you it starts at 124, and the ACK range count is 0. This means that everything below 125 has been acknowledged. I'm not going to be able to parse this much more here, but I'm happy to talk about it later. But just understand that we're able to represent the gaps going down from 125. So that's what your ACK frame here looks like because of that. The ACK delay is 3125 in microseconds, but shifted. And then you have the largest is 125. And the ACK ranges, in this particular case, there are no gaps. So it just says 0. So at this point, let's say that packet 56, this particular packet that we sent, let's say it gets dropped to the network, right? And the sender wants to retransmit this information. Excuse me. And also imagine that stream 8 was canceled. So remember again that we had stream 5, stream 8, and an ACK frame in this packet. This whole packet is dropped. Stream 5 is continuing. Stream 8 has been canceled. And when QUIC loss detection marks this packet as lost, let's say the last packet that was sent was packet number 74. So packet number 56 is detected as lost. And the last packet that the sender had sent was packet number 74. 56 was sent a while ago. So at this point, what do you think will happen? This is where I would encourage you to respond, but don't do that. As it turns out, there's a lot of time and wastage here. But you might think about what should happen here. In QUIC, what happens here is, well, we want to send stream ID 5. That data is still ongoing. We want to be reliable with that because that stream nothing has happened to it. So we will retransmit that piece. Stream 8, however, has been canceled. So we don't need to retransmit that data. Because it's been canceled by the application, we are no longer going to retransmit that data. The ACK frame is a control frame. We don't need to retransmit it. We may need to send an additional ACK frame now if we decide now is a good time to add an ACK frame, but really the packet doesn't matter. The packet simply tells me all of this stuff was lost. And then control goes back to the scheduler that decides what data to pack. It might pack a retransmission of 5, or it might decide 5 has been deprioritized. We're not going to talk about priorities here either, but the scheduler can decide how to prioritize retransmissions against new data that might be higher priority. So basically, the scheduler controls what goes into the next packet. Loss detection simply marks the packet as lost and the frames in it as lost. That is the end of frames and streams and various things. We are at a point for a break. Sorry that we didn't have a lot of time for Q&A or at all any time for Q&A here, but we will come back to it at the end of the next section. So yeah, we're going to try and reclaim the 2 minutes that we've lost here. So come back by 3:18, we'll start at 3:20. We have a 16 to 18 minute break.
I was going to say, if people have questions and they came up, feel free to ask now as well.
Oh, that's true, actually. I don't know. Can people unmute themselves here?
Can I ask a question?
Yes, absolutely.
I'm Vidhi. So I was thinking about the example that you gave. That's probably not a good example when you're sending the data, right? You don't want to introduce a head of line blocking by putting multiple streams in the same packet. But when you're retransmitting it, let's say you lost a packet, right? Or multiple packets, and you're retransmitting it. Is it like better to retransmit multiple streams in the same packet because you already know there's loss? And if you don't do that, you might experience even more loss and cause more congestion on the network if you split it into different packets.
Right. So that's a strategy. I don't think there's a very clear answer there. What you're pointing out is a tension there, right? If you send it all in the same packet, I think what you're asking specifically comes down to is this to some extent there's a question of chance, but it's also congestion happens at the byte level. So I'm I'm floundering because I actually don't know how to answer that question. There's definitely a tension there. Yeah, go on, Robin.
If I can, I think the problem doesn't really pose itself in practice because you will typically only have one stream frame for one stream in a packet. So if a single packet gets lost, if you want to retransmit that, you will just retransmit that same stream frame, right? You don't really have to start mixing it up. What you mentioned in practice will typically only happen at the edges of streams where you like don't have enough stream data to fill a full packet and you want to backfill it with data from another stream. And that's one of the points that you need to make a decision. Do I risk head-of-line blocking or not? Most stacks do. There's just one stack that doesn't do that.
Yeah, so I actually I would suggest that the better strategy is to packetize them in different packets. Because if it is a question of chance, if it's not a question of load, if it's a question of load, it doesn't matter, because your byte load is ultimately the same. Modulo the quick packet header, which should not be very much. But if it's a question of probability, which it tends to be, packets are dropped ultimately, not bytes. So at that point, you will split the probability into half at least. That you at least one of your streams will make progress. That's my off-the-cuff remark.
Usually when there's congestion, right, like queues are building up. In that case, it's not a random probability. It's a certain probability that you're
absolutely.
going to
no, it's true. What I'm saying is that it is a function of load, and that is a function of byte load. But what I'm saying is whether that packet happens to be the one that encounters a full queue or not is a question of chance.
Right. Okay.
When you cause congestion, yes, it's at the byte level. But which particular packet encounters, you're trying to predict whether that packet will encounter loss or not. And you can't. But
let's assume it encountered. That's my question is, let's assume there were 3 streams, right? And I sent 3 packets on those 3 streams. All the 3 were lost. And now I have to retransmit it. And it's a request packet. It's a small request of 100 bytes on each of those streams. Do I combine them when they are lost, all 3 of them? Do I combine them when I retransmit the 3 streams again?
But if you say combine, do you mean combine them in one packet or send the 3 packets after each other? But you can't combine that into one packet because the packets are already full-sized for one.
It's a request, so it will be a small thing.
It's small request. It's 100 bytes request.
Yeah.
Okay.
I would say you combine them, but that's what our stack does. Yeah.
I think most stacks do that. I think
most stacks do that. Yeah.
Most stacks do that, but I actually think that the right strategy is to not do that. But that's fine. I mean, the point is that if you're going to,
sorry,
go on.
I was going to say, if you're really worried about loss and you're only sending 300 bytes, send it twice.
Yeah.
Yeah, exactly. I mean, you can do a number of things that would be. That's actually what I would do. I'm just saying the right strategy. But yes, I agree. That's actually what I would do.
Yeah.
One of the other things I wanted to mention is that this has to do with the multiplexer that you use, right? If you do a round-robin multiplexer and you have 10 streams and you switch between all of the streams after one packet, so you have 1, 2, 3, 4, 5, changing every packet, and then you get bursty loss at the end of slow start or something, then you're going to lose a single packet for each of these streams. You're going to head-of-line block all of the streams. Right. Well, if you send it sequentially and just say, I'm just going to first send the first stream, and that gets a burst of loss, then the second stream coming after might encounter emptier buffers, hopefully, and that might get through first. So there's a very strange interaction between the head-of-line blocking and the multiplexer as well. Even if you don't mix if you don't mix streams in the same packet.
That's a really good point.
What Ian pointed out, I'm going to repeat that in other words. Why not do both?
Yeah.
You can actually do both in this particular case. I mean, so quickly, our stack actually will do that. If you're at the tail of a transfer, it will. Well, we have a config where you can make it aggressively retransmit at the tail to reduce tail loss, to reduce the latency caused by tail loss, and this is basically a tail loss that you're talking about. And what you would do is, if you have congestion window space, meaning you are not the one, you might be running into a bottleneck, but which is a queue that's full, but you've not nearly sent enough bytes in there to really own the burden of causing congestion, then feel free to send it multiple times.
Okay. Yeah, I think a mixed approach is probably better here.
Yeah.
Thank you.
Thank you for the question.
Is it okay to ask a question now?
Oh, sure. Yeah.
So, and this may be basic, but is my understanding right that a single quick connection would give you roughly the same as what TCPs would give you, and then it's up to some stub code to kind of decide how to allocate that bandwidth across the streams? Like
so in libraries, that's not generally true.
Okay.
So the QUIC protocol does not specify. So I think what you're asking, if I might paraphrase, I would consider it a scheduling question.
Uh-huh.
Is that a reasonable way to paraphrase it? Basically, you're asking if you have condition window, which application or stream effectively gets to use that window, or what portion of it.
That's right. It's more of I guess the abstraction I'm having here is there are many streams sharing a common connection, and effectively taking the TCP fair share bandwidth and divvying it up across the streams. Is that right?
It's one way of thinking about it, but it's not the TCP fair share effectively. In this case, it really is it's a local question, so we don't need to do whatever allocation strategy the library offers. That's what you use. This is where priorities comes into play.
Okay.
Because what you want to do is you want to divvy up that bandwidth based on your stream's priorities, or you want to do something there based on the stream's priorities. And if you have everybody has equal priority, then you just round robin across all the streams. When I say you, I'm talking about the sending QUIC stack, and that is implemented by libraries. What I mean is that the every QUIC library comes with an API, which not all QUIC libraries come with that API, but you have you want to be able to, as a library, you want to allow for the application to specify how to schedule among your streams.
I see. And what are some of the common policies that you have in those libraries? Like one is, I guess, treat them all equal and you do round robin.
So Robin has a whole bunch of stuff on this. He's not here. He's left his desk. Ian can also talk to how Chrome does this, or sorry, the Google servers do this. There's a slew of strategies, and unfortunately, what you want is not just an implementation strategy, because a library is making a static decision. That's not particularly useful. What you really want is for that particular connection, based on the content, based on various things, to specify, hey, this particular object is super critical and it's important over all of these other objects. And you want it to be more dynamic than that. You want the API to be expressible, and you want also for the application to be able to use intelligence about the content to decide how to use that API. So different implementations of different APIs that they expose in terms of how. So one example would be that you ask the application to tell you which stream to schedule from next. So you just punt the scheduler completely up.
I see.
So you can go that far.
So I see. So I, as an application developer, have complete control over how.
Yeah, no, this depends on the library, again, to be clear. And Robin has a better sense for this than I do, because he's been looking into all the other all the libraries and what they do. But yeah, that's in terms of the specification itself. The specification doesn't do anything here. It leaves it up to implementations to expose these knobs, and leaves it up to applications to use those knobs.
Got it. Thank you.
I'm going to stream some music.
All right, I think we're about ready to start.
Hang on. Yeah, one more minute to time.
If you can give me the screen share, maybe.
Yeah, I'm trying to do that.
This time I'm going to remember that I need to actually present the slides instead of just show the browser window. Maybe.
Oh, there it is. Okay. So you should be able to take the screen now, Robin.
Yes, I think that's working. Sanjay, could you maybe mute your mic? Thank you.
All right. It is 20 minutes past the hour. And we are going to pick it back up here at your favorite radio station. I think we are good. Do you want to take it away, Robin? So Robin's going to basically do a QLog and QVIS demo. But before I hand it off to him, I just want to say one thing. This is actually some really lovely work that Robin's been working on. And this is actually fairly critical. As you saw earlier with Wireshark, it's super hard to do this stuff for QUIC if you're simply looking at on the wire stuff. And one thing is that you need the entire packet to be captured, and that becomes very expensive very fast. And yeah, I'll pass it on to Robin to talk about how QLog and QVIS break that.
Yes. You can hear me, right? I'm not muted.
Yep.
All right, good. So indeed, now we're going to look at my favorite topic in my primary work during my PhD, which is QUIC debuggability. And as I alluded to before, the fact that QUIC is end-to-end encrypted is a very big problem there, right? If you want to do analysis on them, you need to store the full packet captures and then later decrypt them. That's fine if you're just using a local setup, but let's say you're a big CDN and you want to do in-network debugging or analysis. That's much more difficult because you would first need to find storage space, and you would also need to store your decryption keys, which kind of undoes the whole ephemeral key thing we have going on in TLS in the first place. And then the problem is that if you decrypt the QUIC trace, you're not just decrypting the QUIC metadata that you probably want to look at, you're also decrypting all the user data in the HTTP tree layer, which is of course terrible for privacy. So one of the possible solutions that we've been working on is to use logging at the endpoints, right? So you're not just going to use in-network captures, you're actually going to have the client and the server themselves outputting logs. That has many advantages. The logs can be smaller because they can only log what you actually need. And you can also omit all the user data to be better for privacy. One of the other things is you can also log internal stuff that you don't actually send on the wire, right? Things like the congestion window and the round trip time measurements at the stacks themselves. Very useful to know when you're doing, for example, implementing a new congestion controller. You suddenly get that available for free. There are some downsides, of course. It's still difficult to do in-network debugging for network operators, but let's not get into that discussion too much. That's a whole separate can of worms with the spin bit and all that. So basically, this endpoint logging idea it has been executed practically in two ways. One is in Google's QUIC trace format, which was basically, I think, the thing that they developed internally as well to do QUIC debugging at the beginning. They open sourced that for IETF QUIC as well. It's basically, the format isn't, in my view, very extensive. It focuses mainly on the congestion control and the transport layer stuff. It doesn't have HTTP3 level data. There's only a single tool that really focuses on this format, which you can see here, which is kind of a TCP trace alternative for QUIC. There are currently 2 QUIC stacks that support this, which is Quickly from Jana and Quiche from Ian, I think. So it's definitely an interesting tool to look at. But the main thing I'm going to be talking today is my own projects, of course, which are called QLog and QVIS. QLog is predictably the logging format. This has, to my surprise, become kind of like a de facto standard for doing this stuff. Many QUIC implementations have adapted this, and Jana has even promised that quickly will also add it soon. So nice to hear. And then we have also created the QVIS tool suite, which is basically 5. Currently, we're planning to add more, but currently 5 web-based tools that allow you to load not just those QLog files, also PCAPs and Chrome's netlog files for visualization. That's basically what I'm going to show you now today. If you want, you can follow along with the files you can find at the URL. And this is going to be basically a short, condensed version of my main demo of this, which I'm going to do in the SIGCOMM demo session tomorrow and also on Wednesday. Let's try to get this rolling. The first thing I want to show here is that you can also load PCAPs directly into here. So it's not just for QLogs. So what I've done here is I've uploaded my PCAP and its keys to a public server, included it into QVIS, and if you then just press fetch, it will automatically load those. And if you see something green, it means it works. And you can choose one of the tools here on top. We're going to first look at the sequence diagram. And this is very similar to what we've seen for Wireshark, just visualized in a different way, right? So you just see all the different packets going over the wire sequentially in a vertical timeline. There are some key differences to Wireshark, though, why I think that our approach is a bit more user-friendly. For example, we use different colors, obviously, for the arrows, so it's easier to see which is a client, which is a server. In this case, the client is left, the server is right. So different arrow colors and arrows, but also, of course, for the different frames. So here, the blue stuff is all the actual stream data and the crypto data. The green is the acknowledgements, and then you will also see some red showing up and some more green. And then if we go around, you can actually see the pings are like yellow, and here you can see purple for the flow control stuff. And it's just using these different colors makes it, I think, visually immediately clear that there is some kind of anomaly or like a special thing going on at that point in the trace that you might want to look at. What you can then do is click on these things, just like in Wireshark. And in this case, we're still just showing the raw JSON QLog data, which is kind of what it looks like. It's really straightforward. As you can see, it's just a JSON blob with the necessary information in a human readable format as well. Another nice thing that I find here is that we actually show these kind of periods of inactivity, which makes it clear to see that these are indeed like retransmissions after the first one was deemed lost, but these are actually sent together, and that these things are also sent more or less in bulk. And then, so it makes it easy to track like round trip times across the trace and see which things actually belong together conceptually. The final thing I wanted to show here is, so this is normal. You see that the acknowledgements, that's what I wanted to say, the acknowledgements. so we've seen what Jana explained and I showed a Wireshark is that the acknowledgement frame in QUIC is kind of difficult to interpret. I still have trouble with it to know exactly which of the packets were lost. So what QVIS and QLog do is they make it a bit more clear, I think. They actually list the exact packets that were acknowledged in a given ACK frame, and if the packet is not in one of these ranges here, that means that packet was lost. This means that within QVIS, if you kind of see these ACK frames getting wider, getting larger, that means there are more gaps, more packets that were actually lost at this point in time. So here you can very clearly see the end of slow start on this trace. So packets are being dropped on the network. There's a lot of loss going on. You can visually see this happening. Until when you scroll down, you see it has improved, goes up a little bit again, and then it kind of stabilizes for the rest of the connection, right? So that's kind of already quite nice, but we can do so much better. For that, I'm going to load a couple of QLog files. So if you're still following along, you can just load the QLog files from the web page. You can import and upload them to QVIS. So now if you look at one of the QLog files, you see that here on the left, we suddenly have a lot more extra information that we did have from PCAPs, because this is the internal endpoint state, right? So these are things like the actual recovery metrics that we had. We have the congestion window, the bytes in flight, the RTT measurements that were actually observed by the endpoints. You also have some interesting things here for TLS state at the endpoints that you also don't send over the wire. And things like when retransmission timeouts are set and actually fire. Right. So that's one of the benefits of QLOG. You have this extra data. One of the benefits of QVIS is that because we're now logging at endpoints and no longer just observing the network itself, we can load traces from different points in the connection. So in this case, I have the client trace, but I also have the accompanying server trace. And if you do that, suddenly it becomes possible for us to correlate events between the two to show accurate round trip times. Now some arrows are slanted, depending on how much delay there was. We can very easily now show which packets were lost at which exact moment. We can even show when you had a certain amount of jitter or reordering going on. On the network, you just need to look at crossing lines in this diagram. This is something relatively simple, and you could potentially do this with PCAPs or even with TCP as well. But to my knowledge, please correct me if I'm wrong, there wasn't really a tool available that did this kind of thing. But it's turned out to be exceptionally useful for debugging QUIC's complex handshake in multi scenarios, which is what this is showing. There are some downsides if I load a bit more of a more complex trace with an actual HTTP3 stuff going on. What you do see here is, for example, these are then the HTTP3 frames. So you can actually see it's a headers frame with the different headers, right? As we showed in Wireshark, show up here just as well. If you have a lot of data going on with a long delay like here, it suddenly becomes a bit more difficult to interpret, I'll admit. We're working on that, making it so that you can filter out some of these to make the offsets a bit better, to make it less of a spaghetti situation there. But still, I think it's a useful tool, and it's a tool that most people have been using when they use QVIS. Let's look at the second tool. For that, I'm going to reload QVIS, and I'm going to load the second batches of files that I prepared, which are all with interesting connections. These are a bit larger files, so they take a little bit longer to load, but it should be fine. When they're done, we're going to look at the congestion tab on top. And this is actually basically very, very similar to the QUIC trace tool, and also TCP trace, which you probably know, but with quite a bit more extra information. So if you zoom in here, the blue stuff here are the packets sent, and the green is the packets acknowledged. So the acknowledgements for these packets, time in between, or the offset in between is of course the round trip time on the network. That's basically what you get in TCP trace as well, just a little bit different. These things are up. If you look at the legend, those are the flow control limits, basically the receive window, but here separated out for the connection and the individual streams. So that's all things that you know. Things that we typically don't see in TCP trace, I think, are the actual congestion window, which is the purple here, and then also the bytes in flight, and how they actually drop every time that an acknowledgement arrives, and then slowly go up again as the pacer outputs new packets onto the network. Interestingly, also is here to see, I think, as the actual evolution of the round trip times on the network, as you see the congestion window growing up to a loss event when the round trip time goes down again. All, I think, expected stuff in these situations. So this already, I think, helps with congestion control debugging quite a bit. It also allows you to immediately view some weird stuff going on in these traces. This one, yeah. So here, I think you're going to read at the start. Here, this thing at the start that is just looking really, really strange. At a certain moment, our congestion window stays high, but our bytes in flight simply drop to nothing, and we have a very long resting period. And if you look at what this pink line means, it means that we were actually blocked by the flow control. limit here, where it take a long time to up the stream flow control limit, and as soon as that happens, it can actually start sending more data on the thing. The point is mainly that this is simply immediately visible from this kind of graph, if you're doing this kind of debugging, what the problem was. So it should make analysis a lot faster. Another example that we have here is, no, that's not one. This one. So I can see very bad example of this in practice, where you are almost constantly flow control blocked. The bytes of flight never reaches the congestion window because your flow control, stream flow control is actually never high enough and updated slow, right? Another interesting one is from this one, because it's not always as easy to deduce what is going on. For example, this is a trace from the QUIC implementation, who does kind of an advanced version of BBR, adjusted for satellite networks, I think. And I mean, I'm not a congestion control expert, but I would have been hard pressed to know that this is BBR just from looking at this particular trace. But still, it allows me to observe how things are going on. And these red things, by the way, are packet loss events that happen in this trace. The final one I want to show here is it's called the mystery, because I have absolutely no idea what's going on here. Here also the bytes in flight never reaches the congestion window, but it's not flow control limited. And I was actually hoping that one of you, or maybe Jana or anyone else, might be able to explain this to me. Why does this happen? Maybe not today, maybe tomorrow during the demo. Just to highlight that it's not always, but the tool is very useful. It's not going to be a silver bullet that lets you eyeball every issue immediately, but it certainly makes it, I think, easier to do this kind of analysis. I have to speed up a little bit for the next two tools. I'm going to refresh, queue this again, load the next couple of traces. Like I said, again, there is a more extensive version of this demo tomorrow, so it's not really that big of a problem here. So this is basically what we've been talking about, what I showed earlier. So the way that the different QUIC stacks multiplex the different streams onto this connection. Those were basically screenshots from this tool from different QUIC implementations I'm showing here now. Where here, each of the colors is an individual stream. If you zoom in, we're plotting each and every individual package on the horizontal axis here. So each of these squares is a packet. And this means if you get this kind of a viewpoint, like where you have sequential blocks of the same color, that means you had a sequential multiplexer, which means that each stream was sent in full before you actually sent the data from a different stream, which is very different from next that does the opposite. As you can see here, this is much more like a rainbow, because if you zoom in, you'll see that this implementation is actually multiplexing the different streams on a per packet basis. So each subsequent packet has a different stream contained within it. So this allows you to view that. Interestingly, there are other things that you can view here. For example, you can see here that this implementation mostly does this round robin approach, but sometimes it switches to a more sequential kind of approach. The reason for that is to be found in these black areas. This black indicates that the data above it was actually retransmitted. So you can see here that normal modus operandi for this is round robin. The moment it starts retransmitting, it actually switches to the sequential scheduler, which could be related to the question that Fidi asked during the break, which is how this whole interacts with head of line blocking in QUIC. And that's kind of also where the bottom part of this visualization enters a little bit, where you can see, I don't have enough time to explain all of it, but basically what happens here is that it shows when exactly which byte ranges of a stream arrive. And if you see this kind of outcroppings and vertical black lines, it actually means that there was head of line blocking at this point in the stream. And so that's this visualizations helps you detect this as well. Finally, HTTP3 as Jana said, is experimenting with new prioritization options, and the prioritization system helps you control how this multiplexer actually works in practice. And you can see that here. Here's some of the streams. These 8 are basically being sent sequentially, which is what the HPG wanted to. But these last 2 actually need to send in a multiplex fashion, which you can see the server is indeed adhering to in this case. So especially for HTTP3, this kind of setup is going to be much more complex in practice, and so this kind of visualization should really help to debug this kind of implementation. If Jana doesn't mind too much, I'm going to just take 2 more minutes for the last one.
Yeah, go for it.
Okay, so let's reload. The last one is means reduce is a packetization diagram, which allows us to see how exactly all these different QUIC frames are combined into QUIC packs. Basically, the last thing that Jana explained before the break, where here each of these elements on the bottom, as you can see in the legend on the left, is 1 QUIC packet. So this black area is 1 QUIC packet, and you can see on top there are several QUIC stream frames. The red are each individual QUIC stream frames. What's in them? Well, individual HTTP3 data's. And then on the top shows which frame it belonged to. That's very similar to the multiplexing diagram from the previous part. As you can see here, that for this here, these are all tiny requests, very small files, just 10 bytes in size, I think. And so this server actually combines them into an individual QUIC packet, which, as we also discussed in the break, can or cannot be the best approach, depending on how you look at it. So this is kind of what you might expect to see. What you definitely don't expect to see is this kind of area, because here you have all tiny QUIC packets. These are all QUIC packets of 15 bytes. So the overhead is much more than what's actually contained in them. So a separate QUIC packet for each individual stream data that's being sent. And then interestingly, here there is the end of the QUIC stream is also being sent in a separate packet, even though it's just a single byte to indicate this. So this was it's actually a problem in Ian's stack that we reported, and I think they fixed it by now. This is a different type of trace that I will explain in the demo tomorrow that shows a bit more complex thing going on with packets filling up, backfilling full QUIC packets with data from other streams, as you can see here. And the last thing I wanted to mention is that some of these visualizations also work for TCP, TLS, and HTTP2, which you can see here. Here, the black things is a TCP packet. We have TLS records spanning multiple TCP packets, which you don't have in QUIC, but you do have in TLS or TCP. And then, of course, HTTP2 data frames and how they work as well. So with that, I'm going to give back presentation to Jana for the next part. Thank you.
I think this is going to be Ian. Ian, do you
Yeah. I will present. Do you want to start immediately, or?
Oh yeah, let's just give a minute.
There was one question on Slack about whether it's possible, Robin, to automatically detect the bottleneck at each period, whether it's flow control, congestion control, retransmissions, headline blocking, etc. Any thoughts on that? I have answers, but I'd like to hear from you.
I'm sorry, I was actually reading the Slack and not paying attention.
Oh, just read the question and that'll make more sense. Yeah.
The acts being reordered confusing the analysis. How do you put them back in order?
Oh, I was referring to the most recent question, just that got posted at 3:41 p.m.
Oh, okay. Is it possible to automatically detect a bottleneck at each period? Yes. This is definitely something that we're looking into. It should be easier for us if we let the stacks log that themselves, but then we need to update the QLog format, which is one of the options. We could try to deduce this automatically from what we currently have, but that's going to be heuristics based. We do this already a little bit internally in the congestion graph and the multiplexing graph to determine retransmits. So it's possible, it's planned, but it's definitely not in there yet.
Yeah. One thing that I would add is even if you can automatically determine what the limiting factor is, there's still some debugging as to know why, right? Maybe congestion window limited is completely sensible in some circumstance, and in other circumstances it's unexpected. So I think that's where the visualization tools really have a huge amount of value in my experience. Cool. All right. Okay, I'm gonna begin, and I think this section will be a little bit shorter, so I don't think we'll have time for questions at the end. But as I said before, my name is Swett. I'm going to talk about some of the next few topics, mostly around congestion control and loss recovery, and then also trying to do a quick code tour of the Chromium BBR code if we have time. Jana is going to show you some code as well. But first, we'll start off with quick loss detection and congestion control. First, I want to begin with some terminology, just to make sure I don't confuse anyone. Sometimes I will use ACK, sometimes I use acknowledgement. For the most part, these are interchangeable, and it's just a matter of personal preference. But acknowledgements do come in multiple different formats, and obviously TCP's format is different from QUIC's, as we'll talk about a little bit later. Loss detection is pretty simple. It's detecting when packets were lost. Recovery is a little bit more subtle, particularly in QUIC, but it's basically when you decide that something was lost, and then you decide to retransmit data and have it acknowledged later. RTO stands for retransmission timeout. That's a concept from TCP as well as some other transports. It's basically what happens if you have not heard anything back in a long period of time, and you just send something as a probe to try to figure out, or to try to either induce recovery or as a probe, depending on the circumstance, and we can talk about that. Tail loss probe is a way to kind of recover a little bit more quickly in some circumstances. This was added in TCP a while ago, as we'll talk about later, at least in implementation, and it's only recently started making it into IETF specs. And finally, there's probe timeout, which is kind of what we're calling the quick merger of TLP and RTO. And I'll talk about that in detail later. But really, the goal is to encompass many of the same reasons why you might have either an RTO or a TLP in TCP. Cool. To provide a little bit of background, I know many of you are very familiar with TCP, but I'll go over a few points to start. So in RFC 793, the kind of loss was fairly simply declared. A receiver sends an ACK every time packet is received. When the acknowledgement number stops increasing, then packets are retransmitted because obviously no forward progress is being made. And hopefully after a round trip later, that data is acknowledged. So one big negative of this scheme is you can only recover from one lost packet per round trip because you're only receiving one piece of information, which is that cumulative ACK point, as it's called in 793. And then the retransmission timeout, or RTO, fires at the smooth RTT plus 4 times RTT variance later if no feedback is received. So if you don't only get 2 dupacks, or if you don't get any dupacks, then you just have to retransmission timeout. This collapses the congestion window to the minimum and immediately declares all packets lost and sort of starts over again. So this is a pretty effective strategy, but it also is kind of like the scorched earth strategy in terms of recovery. You declare all the state you have largely useless and start all over. So in 2018, SAC was added, or SAC stands for Selective Acknowledgement, to be clear. And this allowed you to specify multiple byte ranges beyond the cumulative ACK offset that had been received. So there's this concept of FAC, or forward acknowledgement loss detection. So instead of waiting for 3 duplicate acknowledgements actually being received, you can declare a packet lost if a packet, sent 3 packets later is acknowledged. Around this time, adaptive reordering threshold also became much more common because you had a lot more feedback of information. So as you can see here on the right, the SAC option has like a number of blocks, and then you have a right and left edge. And these are all in bytes, of course, because it's TCP and it's sequence numbers. Next slide. So now there's an ongoing draft to do what's called RAC. That stands for recently acknowledged. And RAC changes from, it builds on SAC, but changes to actually say, okay, we know sequence numbers and those are great and those are for delivery, but we're actually going to try to construct a time-ordered sequence of when packets were sent or when data segments were sent. And then do recovery and loss detection in that time threshold. And this is much more similar to what QUIC actually does. It also is the first IETF spec, at least that I'm aware of, to describe tail loss probe. Previously, it was in a paper and also implemented in Linux, but it was not actually in an RFC. But the nice part about RAC is it's built on all the existing TCP signals. So, any sender can unilaterally deploy it without having the other peer change. One minor deployment nit is that it does greatly benefit from the use of timestamps in TCP. And that option, though fairly widely deployed, is not nearly as widely deployed as SAC. So there is some deployment challenge there. Cool. So let's talk about QUIC. Most of this, and also specifically the differences, are highlighted in the recovery draft. The ones we're going to talk about today specifically are monotonically increasing packet numbers. So we've talked about that before, but we're going to talk about it again because it's extremely important. ACK blocks instead of SAC blocks. These are fairly similar, but they are also so fairly different. So I want to kind of go over some of the differences. Probe timeout replacing tail loss probe and RTO. ACK delay and max ACK delay. Talked about separate packet number spaces during the handshake, and the concept of persistent congestion, which is an alternative to the RTO kind of response that TCP uses. All right. So if there's one thing you need to know about QUIC loss detection and recovery, knowing that QUIC packet numbers are monotonic and unique is one of the most important things you could possibly remember. So QUIC uses packet numbers to indicate transmission ordering, opposed to TCP, which uses sequence numbers, which actually indicates delivery ordering, or the ordering of the byte stream itself that it's trying to deliver. So because QUIC uses streams for delivery order, it can use packet numbers to indicate transmission order. So this makes retransmission ambiguity largely go away, or completely go away, really, and it just makes loss detection and loss recovery much simpler. Additionally, because this is built in from the start, you don't have to kind of implement code that deals with, well, what if you don't have timestamps, or what if you don't have the SAC option, and other such things. Another thing to remember is that QUIC packets are never retransmitted, in terms of the same packet number is never intended to be retransmitted. So you can retransmit data inside packets, but not the packets themselves. There's an asterisk on that because technically the very last packet in the connection, we say you can retransmit this because it's a connection closed packet, and at that point you've thrown away all the connection state, and you can't generate any more packets anyway. That's kind of a special case, but yeah, figured I'd call that out. So this makes a lot of things in the QUIC loss detection and loss recovery system much simpler. So let's talk about ACK blocks. ACK blocks are essentially, instead of sequences, or ranges of sequence numbers, they're ranges of packet numbers that are being acknowledged. So the number of blocks is pretty much limited by the datagram size. As you saw in Robin's trace, you can have quite a number of them, and that's fairly common, especially when, say, falling out of slow start and inducing a lot of losses. So, 5 or 10 is not uncommon when exiting slow start. This also means you can detect a practically unlimited number of losses. So much so that your congestion control really needs to be implemented correctly in certain circumstances where in TCP maybe you could get away with being a little bit too aggressive and inadvertently. So there are certainly cases when you can detect, say, 100 packets lost with a single acknowledgement. And in such a case, understandably, you would not want to immediately retransmit all of the lost packets because that would be rather disastrous. So we prefer to include the most recently received packets. So that ensures that there's continuous forward progress. So even if a peer decides, I'm only going to send back, say, 3 or 4 ACK blocks, those should be the ACK blocks that have the most recently received packets and the newest, freshest information. So unlike TCP SAC, you can't renege ACK blocks, so decide that you didn't receive them after you decide that you've received them. As long as the peer has acknowledged a packet once, it's always considered acknowledged. And for example, you can remove it from your send buffer if that's the limiting factor. And just generally, like, it's there. You don't have to go back and retransmit it again. Let's talk about probe timeout. So TLP and RTO kind of evolved in TCP. Like, RTO is obviously a very early mechanism. The core concept is you collapse the congestion window, declare anything that hasn't been previously acknowledged as lost, and like restart and slow start. So that means it's key to actually immediately collapse the congestion window. Otherwise, you would send like much too much data. TCP does not immediately collapse QUIC does not immediately collapse the congestion window. Instead, we have a period of time where we retransmit or send new data as a probe to try to get illicit acknowledgement feedback and make forward progress. And only after a little bit more time do we actually declare that we're really in like a severe network congestion and collapse the congestion window, which I'll talk about a little bit later. But the nice part is that every single time a packet is sent on PTO, we get all of the same congestion control feedback that we might need. So the other note is that because basically any packet elicits the same amount of feedback, we can prefer sending new data over old data to avoid spurious retransmissions. ACK delay and maximum ACK delay. So let's talk about actually maximum ACK delay first. So in TCP, you never have a signal about what the peer's acknowledgement delay is. A commonly chosen value, I believe, is still 200 milliseconds, but no one ever actually, the peer never actually informs you what it is. So QUIC chose to actually explicitly specify that in the handshake, and the maximum ACK delay transport param is placed in the TLS handshake, and that tells you what the peer's maximum acknowledgement delay is. And so you can earn your timers based on this, as seen in the previous slide for probe timer. This also enables removing min RTO, which is a huge improvement for many environments, particularly lower latency environments like data centers. So there have been a variety of custom extensions and things like the TCP MAD or low latency proposal, which were put out there. But unfortunately, there's no real TCP equivalent to this at the moment, partially due to the difficulty of sending new TCP options. So, however, in addition to actually having a maximum ACK delay, so you can do things like arm the PTO more accurately, we also communicate the ACK delay in the ACK frame. And that actually says, like, this was a delayed ACK or this wasn't a delayed ACK, and specifically specifies how much it was delayed. And that's used in calculations of the smooth RTT and RTT var in QUIC. Separate packet number spaces. So that in QUIC, as we talked about before, there are initial packets, handshake packets, half RTT, 1 RTT, and 0 RTT packets. Where half RTT and 1 RTT really are the same thing, but they have some intricacies that are slightly different. So as a result, all these different packet spaces have different keys. As a result of having different keys, you actually can't acknowledge a packet from a handshake if you only have initial keys. You actually typically can't even see what the packet number would be. So even if you tried to acknowledge it, it wouldn't work because of packet number encryption, as Jana talked about previously. And so as a result, if you receive a packet but you can't acknowledge it, then how would it doesn't make sense to declare it lost. And so we decided to have separate packet number spaces where, kind of as illustrated in the bottom of the example, you might send initial packet with packet number 1 and a handshake packet with a packet number 1, almost at the same time, and maybe another handshake packet with packet number 2. And then later on, you might send an initial with packet number 2. If the initial with packet number 2 got acknowledged, it might be sensible to decide whether or not the initial with packet number 1 had been declared lost because it was sent previously. But it doesn't make any sense to make any declaration about whether or not handshake packets were lost, because even if they were sent long before, you don't know if the pair is the keys. So in practice, this is ends up shaking out fairly cleanly, but it does require these 3 different initial handshake and application data packet number spaces. But loss detection is per packet number space, but congestion control and RTT actually span packet number spaces because it's all the same path. And that's really the core goal. So this is really about different encryption contexts and the fact that different encryption keys are required in order to process and acknowledge the packets. I'm going to pause for a moment because a number of those topics are moderately complex, and I didn't know if anyone had any questions while I was going over them that I missed.
Someone had raised their hand, but I am uncertain if that was deliberate or not.
Okay. I will keep going for now, and then I'll pause at the end. Cool.
Yeah.
Great. Let's talk about congestion control. This isn't quite a bit simpler, in all honesty. So QUIC uses new Reno-style congestion control. From a spec perspective, this is great in a few different ways. Number one, at the time the QUIC working group started, it was the only congestion controller that actually had an RFC issued for it. Another is it's quite simple to understand, and it still works relatively well. So it's additive increase, multiplicative decrease. I have this nice little diagram in the lower right about slow start and then the sawtooth pattern that follows. This is very much the same sort of graph that Robin showed earlier with QViz. So thank you, Robin, for doing that. In slow start, the congestion window increases on every acknowledgement by the size of the packet being acknowledged. In congestion avoidance, increases by 1 packet per acknowledged congestion window. So basically 1 packet per round trip, assuming you're not application or flow control limited. And then upon loss, the congestion window is halved. Very well tested, tried and true congestion controller. What is new, however, as I mentioned a little bit before, is persistent congestion. So as I mentioned before, QUIC's PTO does not immediately collapse the congestion window. As a result, not only can you send probe packets, but you also can send other new application data packets. This can actually indefinitely extend the PTO. So you can't, for example, wait for the second or third PTO to fire in order to declare persistent congestion. You could actually enter a black hole period where maybe nothing was being acknowledged for 20 or 30 seconds and never notice it if you were waiting for a PTO fire, just because the application could trickle out data like a ping every second or something like that. That's very slow. So this uses a time concept and says like, if packets are lost over a long enough period of time, which is equivalent to the 3 PTO period, then you declare persistent congestion and collapse to the minimum congestion window. And the idea is that the 3 PTO period is somewhat equivalent to TCP TLPing twice before firing the RTO and then collapsing the congestion window. So all the goals here, even though we specify new Reno, are that the signals are very generic. In the pseudocode in the recovery draft, we have methods like on-packet sent, on-packets act, congestion event, which is now going to be on congestion event, when a packet is lost or is ECN marked. So really, you should be able to implement anything from QUIC to BBR, BBR-v2, any reasonable congestion controller that's out there based on these existing signals, and it should be fairly straightforward. Yeah, that's fast. So that's the end of that section. I realize we're still a little behind on time, but why don't I ask if there are any questions?
Yeah, folks should unmute and ask if they want to ask. But this is also, we can also make this like a 2-minute break here.
Yeah, why don't we make this a 2-minute break and yeah, come back at 4:08.
So I think this is Viri again, sorry. So I think it's important with QUIC, as we are saying, that we don't need to reduce the congestion window when there's a blackout or anything. I think the important part here is to notice that we are saying that we are enforcing or recommending pacing with it, because without pacing, everything else, it just, without pacing, it is going to create a burst, right? If we don't declare persistent congestion after this blackout period or an idle period.
Yeah, that's a great point, Viti. QUIC does have a flows should pace, and then if they are not going to pace, basically they must do something to limit their burst sizes to something that the network can handle and is not going to overwhelm the network. And that's a very good point. And I almost did make slides for that, but did not end up doing so because I realized at the last moment. But I think it's an important change from TCP, because we are not in this recovery draft recommending slow start after idle, as you said. And so as a result, when you're coming out of idle, you really need to do something in almost all circumstances to ensure that the burst isn't too large to overwhelm the network. And typically that being pacing.
Right. Because we don't implement pacing, so we do this idle period, we reduce the congestion window or things like that.
Yeah, just to add to that, the slow start after idle has largely been basically not used because it ends up being a terrible performance degradation at the servers that use it. So it's not used, and we recommend pacing. Not just we recommend pacing, we expect that implementations that don't pace have some way of managing bursts, because it's 2020 and this is not rocket science. We've known this forever. There are two people who raise their hands. Sorry, go on.
I was going to call out that as much as possible, QUIC really tried to build on existing TCP RFCs, but there were cases like the slow start after idle issue where if implementation so commonly deviated from the RFCs, then we certainly didn't want to carry forward a decision that was made years ago and is obviously not being followed. So we wanted to also be very aware of kind of the reality on the ground and the reality of deployment. So at the end of the day, if deployments did one thing and the TCP RFC said the other, then typically we did what the deployments did.
There are two people who raised their hands. Please, I'd say, do you want to take questions now, or what do you want to do, Ian?
Hi, can I ask?
Well, yeah.
Yeah, so my question is that in case of a loss event, the QUIC doesn't seem to back off immediately. So how does the fairness aspect to the TCP on a bottleneck link comes into play?
So are you speaking Which QUIC are you speaking of? Are you speaking of a particular implementation, or because the recovery spec does say, as you saw, that you would immediately have the congestion window using a new Reno style like congestion
So
control.
maybe I can answer this slightly different. Yeah, that's so, Danny. That's not what Ian said. What Ian's point was that with losses, ultimately, what happens on a loss is a congestion controller decision. So that is, if you're using Reno, then you want to back off. If you're using BBR, you might do something different, and that's true across the board. That's true for TCP. That's true for QUIC. The specifications, to the extent that one cares about the specifications themselves, just require you to do the same thing that TCP does right now with TCP Reno. But if you were to implement BBR for QUIC, then that is going to do something quite different on a loss. And that's a fairness question there is really between the congestion controllers, and it's not about the protocol behavior.
Okay, thank you.
Yeah, I would agree. If anything, TCP has too long been conflated with its congestion controller, and they are really separate things. And hopefully, QUIC will make that clear.
There's maybe we'll roll along and people can maybe ask their questions later. We should probably continue.
Yeah, we have plenty of time for questions at the end. Oh yeah, this is you, Jana.
Oh, am I picking it up here? Do you mind just keeping the slides so we don't have to? Sharing one. Yeah. All right. Well, welcome back if you're on your break. And we are now going to talk about congestion controllers in QUIC in general. There is no, so what Ian just alluded to is actually useful here. We've always known in TCP as well that congestion control is a separate aspect of the transport. It's effectively a pluggable aspect of the transport. The Linux implementation, the FreeBSD implementation, they all, over the past 10 years at least, now have pluggable, the ability to plug in new congestion controllers as you want. And that's basically how QUIC sees it as well. The implementations we are going to talk about, I'm just very briefly going to talk about what the quickly interface to congestion controllers looks like. And the part of this conversation here is to show you, as researchers, you might want to implement new congestion controllers to QUIC. Every library ends up being different, because in QUIC there is no one implementation. Just as with TCP there wasn't one implementation, but there are only a handful of operating systems. With QUIC, however, we're going to have a large number. We have a large number of implementations, and each one of them tends to have its own interface. So that is perhaps a bit unfortunate, but it is also goodness. We see that as diversity in implementations that's valuable. So the first thing I'm going to do is just talk about quickly, which is the Fastly implementation of QUIC. I mean, you see what we did there. My company is Fastly. The company I work for is Fastly and QUIC, and we did quickly. But the congestion controller here, right, has an interface that is good. I'll show you the interface in a second. But the example implementations are also linked there. I'm not going to walk through the example implementations here, but I'll talk about the interface in just a second. The pacing right now is not yet done. It's something that we are working on. We'll get it in there. And contributions are absolutely welcome. We actually recently got a QUIC implementation as a contribution, and that was an excellent contribution. So Leo, if you're out there hearing this, listening to this, thank you so much. And more is absolutely welcome. Next slide. So basically, at a very basic level, this is what the interface looks like in quickly. There's a type, there's a struct that basically gives you the interface, and there are three functions really. You inform the congestion controller when data gets acknowledged. You inform the congestion controller when data is lost, and you inform the congestion controller when persistent congestion is detected. So this is the equivalent of, in this particular case, if Reno were to be implemented, on loss would reduce the congestion window by half, on act would increase it potentially by a certain amount if it's not in recovery, and on persistent congestion should reduce the congestion window to the min window. That's about all. I mean, I guess, do you want me to walk through the Reno code, or should we just go to the next interface, Ian?
Given where we are on time, why don't we go to the next interface and
go on.
And then, yeah, we have time at the end. We'll walk through the congestion controllers more.
Sounds good.
So I'm going to talk about the congestion controllers and the interface in particular in Chromium Quiche. So we have a similar but slightly different interface. One key difference is we have an on-packet sent event. This is particularly useful for congestion controllers like BBR that actually have their own bandwidth estimator built in, because you need to know when packets are sent as well as when they're acknowledged if you're doing bandwidth estimation. We also combine the packets lost and packets acknowledged, as you can see in our on congestion event. It ends up being a little bit easier to deal with these events simultaneously, at least in our implementations, than it is to do them separately. So the big thing is when you implement a congestion controller, besides like actually tracking what packets are sent and when they're acknowledged or lost, is determining whether or not you can send immediately and what the pacing rate is. So in practice, most implementations of send algorithm interface implement can send by returning whether or not bytes in flight is less than the congestion window. So basically, do you have available congestion window? But additionally, there's this concept of pacing rate, which in a Windows-based congestion controller, and by window I mean congestion window based, not Windows like the operating system, just to clarify, is typically some constant times the congestion window divided by the smooth RTT, and that provides a pacing rate. So for example, if you wanted to pace your congestion window over the the current RTT, you would just make your constant 1, and that would smoothly pace your congestion window over the RTT. For bandwidth-based congestion controllers, it's like BBR. It's fairly common actually to have a congestion window that's notably higher than your bandwidth times your RTT. And so you might have, for most of the time, you might have like a unity gain again around 1. And if you're looking for more bandwidth, that might increase. And if you're trying to drain the queue, that might decrease. And that's kind of exactly how BBR works. Kind of goes through like different gain cycles. Put a link here to BBR as well as a link to the paper. One thing I will note is if you spend some time going through it, obviously there is this internal bandwidth estimator, which is very, very important to BBR. But in addition to that, there are also a number of experimental options littered throughout the code. And so if you're confused about why something does something in some circumstance, it's worth being aware just that there are a huge number of experiments that have been done on BBR, many of which are not active. But just that probably adds some unnecessary complication to the code over what it normally would be. Cool. And we are now back on time. Why don't we come back at exactly 4:20, and we can finish the last kind of section on extending QUIC. And
we want to just go through, Ian? We could like finish up and go.
I am happy to go through whatever. Sure.
I think let's just go through and we can get a break and then come back with Q&A. Yeah.
Okay, that sounds great. Cool. So QUIC uses transport parameters to negotiate extensions. That can be anything from a simple bool or something that has a 1 or more values that are, is fairly complicated. So you really need to use transport parameters when negotiating an extension because if you send an unsolicited and unnegotiated frame to the peer will close the connection on you. So QUIC is not TLV or LTV or any of the other formats that might allow you to ignore an unknown frame. So unknown frames are treated as an implementation error and cause connection termination. So the first example I'm going to go through is how to change the acknowledgement frequency. So QUIC follows TCP RFC 5681, which recommends acting every 2 packets in practice. Various implementations don't do this in a wide variety of circumstances. In particular, they tend to send fewer than that number of acknowledgements in TCP. Sometimes this is end host. It's also done by middle boxes. And some of these optimizations actually turn out to be fairly critical in the wild. Because QUIC packets are encrypted, middle boxes can't really do this effectively because they can't actually see what is an ACK and what is, say, just a small data packet. And so we propose an extension to allow changing the acknowledgement frequency. So the real goal here is we have a frame that's sent from a sender to a receiver to change the receiver's acknowledgement behavior. So if you're going to see in a moment, the 2 things we really wanted to change were the ACK delay. So currently that's communicated, or sorry, the max ACK delay. Currently that's communicated at the very beginning of the connection. But if it turns out, you don't know how long the RTT to the peer is, and you send, say, a 50 millisecond max ACK delay, but it's actually like the peer is 5 milliseconds away, maybe that's an inordinately long period of time to wait to send an acknowledgement since it's 10 round trips. So you might want to decrease that at some point in the connection. Additionally, later in the connection, you might want to greatly reduce the acknowledgement frequency because you already have a fairly large congestion window and you don't really need the feedback as often. So here the transport parameter is a min ACK delay. So this is a case where we didn't just use a bool, we actually use this to specify the minimum amount of time the peer would tolerate in terms of ACK delay. So that avoids me requesting you to have like a 0 millisecond or 10 microsecond ACK delay that is just impossible given the timers that you have. So we lay out the frame here. If you want to know more details, it's definitely better to look in the draft. But it's a pretty simple concept, and it's as I think Jana pointed out before, all these i's are variable length integers. QUIC loves variable length integers, so pretty much everything's a variable length integer. And then you have to obviously define your own frame type and get that approved. So the other example is unreliable sub-packet payloads. So QUIC provides and HTTP3 uses streams for all the data being exchanged between 2 endpoints. Streams are by default reliable. So as you saw in Jana's example, you don't actually, if the stream is canceled, you don't actually need to retransmit all the data. But the default mode is reliability. So datagram is kind of the opposite. It does not span multiple packets. It is not flow controlled. It is unreliable by default. And it is congestion controlled, but it's kind of the opposite stance. It's a very, very simple mechanism. It's used for a wide variety of circumstances. There are things like VPNs being proposed over it. People have proposed, mapping RTP onto it. There are a variety of other things. But its simplicity is definitely a benefit because you can kind of put anything that you might even put on UDP on it. So in that case, we negotiate it with a max datagram frame size. So that's the max datagram frame size in bytes. This is there because, in theory, one might actually have multiple different layers of QUIC tunnels. And you want to kind of ideally ensure that your datagrams get all the way end to end. And they're not really meant to be fragmented since they need to fit in a single QUIC packet. And here's the frame. It's basically type, byte, length, and zip data. It's pretty simple. It's like a massively simplified stream frame. Cool. And that's all for extensions. Does anyone have any questions specifically on extensions before we go into general Q&A? Because
you go ahead and unmute and ask if anybody wants to.
I got a question.
Yep, go ahead.
Okay. Has FAC, forward error correction been considered again to be added to QUIC in IETF?
Yeah, definitely. There is actually still an ongoing draft that I was once actually involved in, but I am not at the moment. but I believe actually some people on this call are involved in. Marie's Jose Monpetit, she is still on, maybe not, but yeah. So I think the only question there is forward error correction. I think an application level feature or a transport level feature, and I think the only way you can find that out is to kind of build it. But it's certainly an area of interest and might combine particularly well with datagram. It's hard to tell.
Thank you.
Sorry, the ACK frequency is the extension frame, right? And is it part of the draft right now, the quick drafts?
It's an individual extension at this point. It's not yet part of the quick drafts.
Okay.
Yeah. Datagram has been adopted and is in the charter now, but ACK frequency is not yet in the charter.
Okay.
For those following along but not really at all aware of what this conversation was about, this is IETFisms. We are basically talking about what the working group considers as accepted work and what it is not. But yeah, just bring everybody else up to speed.
And could you just a little bit, maybe you have spoken about this before, but with the experience with ACK frequency, like what kind of frequency is good for the stack, at least for your experience?
I've mostly experienced with like numbers like 10 and 20. I don't think there's a reason that you couldn't particularly go higher, but it sort of depends on the congestion controller. So the thing I found, at least early on, was that congestion controllers like Reno that are window-based are more sensitive to receiving frequent acknowledgements than those like BBR, which naturally are trying to run non-congestion window limited. And so one might have to be a little more careful if one is using a congestion window-based congestion controller.
Okay. Does it
Jana
make
has thoughts, I'm sure.
Sure.
No, I mean, I think this is part of the reason we are writing this this draft, is to basically, this extension is to allow implementations to experiment with this and come up with strategies that make sense. Because as Ian pointed out, the controller in play also matters a lot. How often you acknowledge, if it's a window-based controller that is doing perfect, what's the word I'm looking for? Packet conservation, then timely acts are super important. If the sender is more lax on packet conservation or has tolerance, then it gives the receiver a little more leeway in how much it can, how long it can wait before it sends an acknowledgement. So that is why the communication in the extension looks the way it does. And our hope is that people will experiment with this and play with this and find what the right answers are for their own controllers.
Okay. I was wondering if it makes more sense, instead of like a number of packets per ACK, instead of that, it's more on the cadence of time, like on the basis of, if I receive 100 packets, at a time in my stack and I'm able to process it, I just send one ACK. Like I don't have to really send 10 ACKs for 100 packets.
Yeah, there is actually an explicit optimization called out in the transport draft about if you are able to receive a number of packets, whether it's 10, 16, whatever, all at once, and process them all simultaneously, say they're sitting in a UDP receive buffer, then it's typically recommended that you send one acknowledgement for those.
Sounds good.
Regardless of the extension.
Thank you.
Yeah, because as you point out, TCP implements this sort of optimization widely with things like, LRO, GRO, and this is some of what generates these larger acknowledgements in TCP.
Right, exactly. I mean, with optimizations, now we're going to look more towards optimizing stuff, right? Like crypto optimizations and ACK and offloading segmentation. There's so many things to do. So those things are going to, surface more now.
Yes. I would say, Vidhi, to your point of packets and time, the extension actually specifies both. So when a sender says to the receiver, hey, use this as your ACK frequency or your ACK rate, it's basically saying ACK 1 every n packets, That's one bit of information. The second bit of information, it says update your max ACK delay, meaning can you please change your ACK delay, the maximum amount of time you wait before you send an acknowledgement, to be X milliseconds. And between those two things, we try to capture the packet and the time events both.
Okay, sounds good.
All right. Do we want to take a moment and then come back to Q&A, or should we just go to Q&A? We can open the floodgates and the floors and have a bloodbath here. People can tell us why all of this is a terrible idea.
I would propose taking a small moment.
Okay, let's take a moment then. We'll be back in a couple of minutes, and we'll have half an hour for Q&A. So prepare your questions. And we, just to be clear, I honestly, I don't think we need to really, we'll moderate this to the extent necessary, but I would say find a sensible time, just raise your hand, not raise your hand, sorry, just come in and unmute and ask questions, because it's going to be untenable here. We have right now 77 people left on the call.
Feel free to ask questions that are outside the scope of this particular talk, but are related to QUIC as well. Like, certainly we've, there's things about, for example, like, just what we were talking about, like CPU optimizations and LRO and GRO and GSO and all those things, and how like optimizations in TCP like do or don't exist in QUIC. I don't know. There's a lot of topics that are outside the scope of what we talked about today. So feel free to ask anything, and we can, do our best to answer.
All right, we'll take 2 minutes now. All right, we are waiting for Robin and Ian to get back. But we can get started, I suppose. I would say, if you want to ask questions, don't. At this point, I would say just come up to the. Oh, there's Robin. Robin's back, and I can see Ian showing up as well. Okay, so they'll both be here. Just come up and ask questions. Do we need to? Well, let me moderate to the extent possible. If you want to ask a question, let's just on the Zoom chat, not on the Slack chat, on the Zoom chat, put a +Q, and I'll throw you into the queue. Sanjay, you have had your hand raised for a while, so I'll put you in there first.
Yeah. Actually, I'm wondering if we can have some discussion on more on the
Sorry.
Sorry, I promised a wardrobe change. I did not mean to interrupt your question.
Yeah. So
much better.
I think in the last segment we talked about RTP very briefly. Do we see could we implement something like Google congestion control on top of QUIC? You see what I'm saying? So something for the audio video conferencing.
Yeah. So
yeah.
I don't know if it's currently available, but we did actually implement GoogCC on top of QUIC a while ago. I can try to see if it's open sourced at the moment, but it definitely got implemented. Trying to think. There are a few quirks about GoogCC that make it a little bit of a challenge, but it's definitely possible. It's mostly around the way they're manipulating the pacing rate is not always event-based. Sometimes it's like non-event based, like just time-based. And so you have to add a little bit of complexity there. Oh, sorry.
We can finish up that. Yeah. So basically, yeah, between datagram, between the datagram extension and this datagram gives you unreliability, and you can plug pretty much anything into the congestion controller. It's a congestion control. It's congestion control. It's got very little to do with the rest of it.
Yeah. Thank you.
Thanks, Sanjay. Sergey, you're next.
Yes, Jana. I have a couple of kind of questions or comments on this point that QUIC doesn't have a standard congestion control. So essentially, people can plug in different congestion control algorithms. So in congestion control area, there are bitter disputes which algorithms are more efficient or more fair. So do you have any concerns about it? So what disputes about what's more efficient and fair? No, QUIC Reno, QUIC BBR. And do you think about some notions like QUIC friendliness?
So I'm sure Ian has thoughts on this as well. My high order point is going to be this, that we specify a controller for the RFCs. So when you're talking about the standards, right, like 793, like different RFCs for QUIC, we are going to have a congestion controller specified. That is not going to reflect reality, just as it doesn't reflect reality for TCP right now. The world is still quite diverse in terms of the deployments of congestion controllers you see. There's actually a very, very good paper from a student from NUS Singapore last year on what it calls the a survey of congestion controllers. Basically, he built a tool that could detect what congestion controller server was using. This is for TCP, and it's an absurdly lovely tool. And he finds a very nice set of controllers that are already deployed. Effectively, server deployments control the kernel. So Google can deploy its own thing, as it has done in the past. It has deployed BBR. Fastly can build and deploy its own congestion controller. Akamai has built and has deployed its own congestion controller. there are congestion controllers already being used quite extensively that are very diverse from each other, and sometimes at odds with each other, as you're pointing out, Sergey, in terms of their end goals and what they're doing. So this jungle is already full of different kinds of animals. QUIC makes it a little bit easier, perhaps, because the application allows you to do that. But I really don't think that's where most of your problem is. The problem you're right in pointing out that there is a question here, and I think we should look at that. But that is protocol agnostic. It is a congestion control question. It's a broader question.
Yeah, I would agree with what Jana said and add a few points. One is for most OSs like Linux, with the set sock opt, you can switch from QUIC, which is default in Linux, to Reno or BBR or some other congestion controller. But there are other sock ops that are typically also not protected that allow like other changes that one may or may think are appropriate. But then there's the discussion of what fairness means is a very complicated discussion that I think is well outside the boundaries of QUIC. And I don't think even like the various IETF working groups devoted to congestion control, ICCRG or whatever, really have a good handle on it. So I think it's hard, but yeah, it's definitely like it's not a QUIC thing. It's definitely a congestion control question in general.
Yeah, I'll also say very quickly that TCP friendliness was always a misnomer. It really wasn't TCP friendliness; it's Reno friendliness. And if you cast it that way, then the question itself changes in your mind. Right? Do we really care about Reno friendliness? Shouldn't it be more QUIC friendliness, or should we care about QUIC friendliness and those kinds of things? So
yeah.
I
mean, if you do the math on the Mathis equation for Reno, for example, and try to hit say like 1 gigabit, the loss rates required for most RTTs are so abysmally low that you would kind of laugh at them. There's something on the order of I think like 1/100% or something. So the reality is that for modern networks, probably some changes are going to be necessary to optimize for like the networks that exist today.
I hope that answered what you were asking.
Yes,
for,
yes, thank you. Yeah, and I tend to agree.
Vidhi, you're up next.
Thank you. You were mentioning, Ian, about GSO and all those things that we want to do for CPU optimization, right? So, is there a difference between just using send and multiple message and GSO in your experience?
On Linux, there certainly is. There's a huge difference. So send them a message on Linux, actually, you skip the syscall overhead, but it pops right into the kernel and then does the equivalent send message on the other side. So you save only the syscall overhead, which actually is commonly negated by other costs that are hidden elsewhere, like memory cache locality and other things. But so that's where like UDP GSO is a pretty big performance improvement, but send MM message is basically non-existent. Receive MM message actually is better because it's typically easier to use, and we do use that both on our servers and clients when available. And one of the big differences again is like cache locality. It doesn't do anything bad to the cache locality, but different stacks are going to be different. So like Linux is Linux and it's as much an implementation choice of exactly where like the send M message like splits into multiple paths.
Right. I think cache locality is the big winner in all of these when we're processing the packets. And like QUIC, because of the encryption, it has this thing that we cannot do the segmentation offloading, right? Only if we allow the keys to be passed to the kernel, and only then we can allow the streams to be maybe get segmented later on. Like we can just send 64K bytes of data and then the streams can be formed later on. Like, I don't know if there's a benefit to look into it from this angle, like sharing crypto keys to the kernel.
Yeah, so I don't actually know when he's presenting, but in Epic, during the presentations in Epic on Friday, Lars Eggert has a really nice paper that he'll be presenting, specifically where he went through and kind of analyzed a variety of different QUIC implementations and looked at where they were using CPU and where the big savings looked like they would come. And for the ones that were not doing kernel bypass, the big savings was in doing kernel bypass or using something like UDP GSO with hardware offload. And for the ones, well, the one that was doing kernel bypass, crypto offload was kind of the next big savings. And so even with the memory locality issues, it seems like crypto offload, along with UDP GSO hardware offload, would be incredibly valuable.
And that's work that's happening as well. I mean, there are both Intel and Mellanox, at least on the NIC side, are interested in hardware offload of crypto, and they have been in conversations with several of us over the past couple of years at least. So hopefully that'll happen soon.
Sounds good. Yeah, I'm looking forward to it. Thank you.
Use your power to twist their arms.
Yeah.
All right. So Florin, you're up next.
Yeah. Hi, Jana. Do you see any chance in the use of QUIC over a different type of transport? Like, for example, you have GRE going over Ethernet as well as over UDP.
You mean, do we foresee QUIC being used directly, not on
over
UDP,
Ethernet,
but
for example?
Something. I mean, anything can happen, right? But
I know, but
yeah.
I mean, do you see any limitations from QUIC perspective?
Yeah, fair enough.
I'm gonna. One thought I have is that whatever gets the fastest, best implementation is going to end up probably being like the dominant path going forward. And so as we talk about things like hardware, UDP, GRO support, things like that are going to make the UDP path like an increasingly sticky path over something like having a dedicated protocol number or going over a different path. At least that's kind of my view of the ecosystem is whatever the fast path is and whatever the most traveled path is going to end up being hard. It's going to be hard to move it on to something else, and there would be a little incentive to do so.
Yeah, I mean, also in terms of deployments, I think that the design so far at least has has assumed UDP underneath it, but it certainly doesn't need to assume it. I mean, what problems pop up when you don't assume depends on what the underlying protocol happens to be. The only thing we get out of UDP really is demultiplexing, and not even that. So in theory, QUIC should be able to run pretty much on whatever you want it to run on. So yeah. So we'll only know once when somebody tries it what the actual limitations are, but I don't believe we have any fundamental design limitations. The next person, I do not know how to read this name. I'm not going to try to do that. Gao.
Hi. Yeah, it's a great talk. I have a few questions. The first one is, I found you mentioned that the QUIC supports the output buffer management, like the scheduling between different streams. I was just wondering, do you have more like details how we can implement those? Are them the APIs that open to the user, or you have like the default mechanism between the like multiplexing of the different streams?
So at a high level, this is a question that we don't really get into specifically within QUIC, because ultimately the question that you're asking is one of how do you apportion resources to different streams or different pieces of data that are going over a QUIC connection. And the short answer is that really depends on the application. So to the extent that you want anything standard there, it would have to be the application that decides what you want to do, if the application protocol has any specific notions there. In general, though, in terms of implementation, every library or implementation is going to expose its own API and its own knobs that the application sitting on top of it will control. There is no uniform way of doing this at the moment. And I don't think there's an intent to make this uniform either. Every library is going to expose, much like the condition control interfaces you saw there. There's going to be, functions should be roughly similar, meaning that I should be able to tell an implementation, hey, I'd like to prioritize X over Y and send this now, things like that. But at the moment, there certainly is no standardization of the API.
Let's say just like every application is like containing for the different streams, like they're all full of data to transmit, and they are sending them to the NIC. Does the QUIC can handle them in a fair way, like within the same host, or it is just up to the application that they should control their output speed?
It's up to the implementation of QUIC. So this is, the question here is what kind of scheduler should you have across streams, right?
Right.
If your streams have infinite data, what scheduler should you use? And
exactly.
If you have no information at all, a very simple implementation that has no information at all would simply do round robin across these things. And most implementations do that, but we don't specify that anywhere.
But we can program them by our own, right? By the user.
Yes.
Thanks.
Yes.
And just a little bit more, like, does the QUIC support like different stream using different congestion control at the same time?
That is not recommended or specified, because that is, there is no use case, at least that I can foresee, where that would end up being a net win, because you're basically going to end up competing with yourself, right? And
yeah.
if you compete with yourself, then you're better off actually trying to schedule and not cause yourself loss and congestion.
Yeah. So I want to give a moment. I just want to one clarification, and then I also want to say, Robin may want to say something about the scheduling, the multiplexing aspect of this. I want to make this clear that when we talk about is specified or some such thing, what we are talking about really here is what does the specification say implementations should do, what they may not do, what they should not do, and stuff like that. That is the specification. That's an abstract notion. It's text written somewhere. What individual implementations do that are compliant to the spec will follow the details in the spec. And what we are trying to point out here is the spec doesn't say how you should do scheduling across different streams. And the reason we don't say that is because there is no right way to do this. But Robin, you may want to say more about this. Robin,
yeah, exactly. So that's kind of like my main research topic. Past few years. So like as Jana says, the QUIC spec itself is very short on details on this, so it leaves it up to the implementations. And most of the current implementations don't really have extensive interfaces for this, because it's difficult to imagine how fine-grained you want something to do, right? How do you expose, like, I don't know if you know much about HTTP2 prioritization, but there you had like this whole complex dependency tree that you can build where you can be very fine-grained in how you want the multiplexing to happen. Do you want your implementation to actually expose this, right? There have been a lot of discussions on what the right way is. Do you keep it very high level? Do you just say priority buckets or something like that? Nobody agrees, and most people, I think, are waiting for HTTP3 prioritization to see what that does, and they will probably just make an interface that can do that, at least in the beginning, and then evolve around that over time. That's what I expect will happen. Most stacks don't really have a good interface for this, as far as I know at this point. But there is nothing inherent in QUIC that this cannot happen. This is simply something you should implement, right?
Thank you.
All right. Sean, you had a follow-up question, I think, to...
It was a follow-up on the congestion, but
yeah.
So maybe more of a philosophical question, but I mean, people learn with congestion very early on. If I have to send a very large file, it's easier to win if I cheat and break that up among 10 TCP connections concurrently. So web, all sorts of application accelerators do that now. Whether or not you think that's a good idea. You guys are sort of in the opposite camp. It's a little bit like STCP. Your ability to do streams now means that you're doing the opposite. I'm going to aggregate a whole bunch of things potentially into the same congestion control stream. And it's not clear to me if there's a congestion control algorithm that really takes that into account. But my more philosophical question is, what is your guidance to people on when, if I want to talk to the same computer on the same thing, do I make that part of the same QUIC connection, or do I jump on an existing connection and be a new stream? If you believe that making the streams fatter tends to hurt the whole QUIC connection relative to everybody else on the path. Any thoughts?
So I definitely have thoughts on this, and I think we all do. You're exactly right that the world out there does funny things, and there are things in the network that do funny things with congestion control and so on. When one asks how many connections should you use, if you remember, there was a time when not even now you can go change the maximum number of connections in your browser per server that you can use, right? It's 6 is the default in Chrome, for example. And there was always the question of what's the right answer. And the short answer is the right answer is always 1. We know that to be the case.
Sure.
Now, can you be wrong with 1 as the answer? And the answer is, yeah, you can certainly be wrong sometimes. But the interesting thing is that there's a lot more that one can do within the congestion control. At a high level, I mean, you asked a philosophical question. So philosophically, at a high level, congestion control is about determining how much bandwidth I have available to send, and about other things too. But one of its core things is determining how much bandwidth I have and how can I send, how can I use that bandwidth, and how can I recover from changes in the resource that I have here, and also how can I allow others to come in and compete reasonably with others. This is best done with most information that with as much information as I can get. Given that there's no offline way for me to learn, the more packets I can pack into one connection, the more information I can pull out of that single connection. So at a philosophical level, for me personally, I get signal out of every packet in ACK. And if I can put everything into one connection, I can build a better controller. Now, if our problem has been so far that we're splitting connections into 5 connections and we are seeing improvement in performance and so on, it's because our controllers have sucked. It's not because there's some fundamental magic with a connection. Although I will point out that there are some people who have in the past done a throttling at the connection level of bandwidth. That is by far not common. So what is common is that your traffic, 5 tuple, whatever have you, your particular endpoint is getting throttled. And you can open 15 connections in there if you want. You're going to be competing with yourself. And if your single controller does not get you the same throughput, then your controller is not doing a great job. So to me, the answer here is not multiple connections. It is work on the controller to make the controller itself better.
There's one thing I'll add on top of what you said, Jana, and slightly contradict one minor point, which is for HTTP2, there is head-of-line blocking for GCP. And so if you do expect to experience loss, then there is, in some circumstance, a cost to using only a single connection. And at some point, there can be downsides. And certainly, I'm not sure if the studies that have found those downsides are theoretical in nature, or if we think they actually bear out in practice on modern websites. And I think we'll find that out with HTTP3 when it's actually deployed. But that there was a cost. And I think with QUIC, that one reason disappears, hopefully. And so I'm hopeful that if anything, QUIC is the reason to only use one connection, because now the only downsides are basically, can you choose the right initial congestion windows / can you choose the right congestion controller, or get your congestion controllers to function effectively. Yeah.
Actually, just to butt in and follow up on Sean's point. So there are kind of philosophical answers to it that more appealing. So Bob Briscoe in SIGCOMM 2007 said that flows or connections are technical constructs and fairness should be done between economic entities. So one solution, which is not particularly popular UA on the horizon is that you get what you pay for, but it's not implemented.
So there are many more questions. We are at the end of our time here. What I think we...
Can I just ask one very quick philosophical follow-up to Sergey's thing?
Using quick and philosophical in the same sentence there, Sanjay, that's dangerous. Go on.
Yeah. No, I think it was about this proliferation of congestion control protocols, right? So now one difference I see is previously it all used to be kernel implementations, right? Whereas now you're making it very easy for anyone, maybe a grad student to create a new congestion control algorithm. So do you see this issue becoming bigger, this proliferation of congestion control protocols? And I was at a Facebook faculty summit 2 weeks back, and they were talking about Facebook experimenting with many different protocols on top of QUIC. So there was this question about, potential for unfairness and things like that.
So there are at least two ways of answering this question in my mind. The first way of answering the question is probably the most sensible one, so I'll do that first. The high level bit is that just because I can write a congestion controller doesn't mean that the bits on the internet are actually that I'll be able to get it deployed. Sure, a grad student can write a controller, user space, kernel space, wherever they want. It doesn't matter. But for internet traffic to actually use that controller is a much, much higher bar.
I see.
Facebook, yes, is going to be working on controllers with QUIC. If they weren't doing that, they'd be doing on it with TCP in the kernel. So, the majority of the players are already playing in this field, right? Like the people who are already working on congestion control in terms of deployment, not in terms of in the lab, are already doing it. This is not a huge bar for them. The thing that it changes is it makes it more agile in the sense of I can iterate more rapidly on the controller. So if you've seen CCP, this is like work that came out of Hari's students, Akshay and I can't remember, Frank. There's this work called CCP. Ian, do you remember what the CCP stands for? Anyways, it's basically, it was trying to pull congestion control out of TCP and into user space. There's BPF work now that's going into trying to, Olivier had his students work on writing congestion controller up from user space for TCP using BPF in Linux. So there's a lot of work happening in trying to move like congestion control and transport functionality up into user space because there's agility there. It doesn't mean that you automatically lose control over what's happening. And the second way of answering this is that we've so far lived under whatever controllers have made it into the kernel, but that is a barrier. That's a very strange sort of a filter, right? It's like I don't know. I think of it as the GREs are for grad school. It's a dumb filter. I mean, fine, it applies as a filter, but it's arbitrary. There's a lot of just because you can write kernel code doesn't mean that you understand anything about congestion control, and because you understand congestion control doesn't mean that you will be able to write kernel code. There's basically an overlap there that's not necessary. So
I'll add two things. One is to be deployed widely, a congestion controller ideally needs to work well under a relatively wide variety of circumstances. And if you look at the things that make most people on the internet lots of money, it's not downloading 100 gigabyte files, which is the type of stuff that would crush the internet if you were massively too aggressive. If everyone is doing that simultaneously, it's a lot of small objects and other resources. So conveniently, there's a huge incentive to make sure that things like, for better or worse, like ads and other small resources are fast. In order to do that, you need to make sure that your buffers aren't bloated and you haven't just caused other flows like a huge amount of loss. And so I think there's a lot more incentive compatibility in this ecosystem than one might appreciate. But I also think that even people who are experimenting are also very cognizant about the impact that they might be having, whether it's on their own traffic or on other people's traffic. And I guess the last thing I'll say is it's surprising how often really there's you are the only person on that internet connection ostensibly. At least that's basically how it works out. So even you load a web page or something, you might get 10 connections, but it's you versus your other 9 connections. It's much more likely you're competing with yourself than anyone else. And so
I'll say one thing in general, that basically one of the really cool things, and this might be of value to you, Sanjay, and generally academics in general, is that QUIC will make it a lot easier for academics to plug in, so to speak, into trying out new controllers. I don't mean that just in the lab. It's a lot easier for us to take in code that comes from outside if you can isolate the fault domain, right? If you send me a kernel module, for example, my kernel folks will simply not allow me to plug that into the kernel. But if it's a module that lives in user space and I can isolate that particular controller, then yeah, it's much easier for me to try out a new controller on my servers. So there's the hope is that going forward we will be able to not just iterate ourselves, but be able to take in code that comes from outside as well, and implement and deploy those modules and try it out and see what happens. So,
and I think like there could be nice educational applications too, right? Like if you want students to do a class project or something.
Oh yeah, absolutely. In fact, one of our early things was for during this tutorial was to actually have folks implement a very simple controller to one of these APIs. And it's actually not that hard because the APIs are available. It's super simple. It's user space as well, so you can combine. You can build and run and test it out within an hour. You could do this.
And I think absolutely the congestion control plane that Jana was saying before, the paper, the congestion. I think it's called CCP, congestion control plane.
Yeah, CCP. Sure. Yeah, congestion control plane. Yeah, that's right.
But the good thing, I really like it because like when we started developing QUIC, we have to write cubic again. And the good thing with CCP is you just put cubic up there, you put Neurino, whatever you want to experiment, and it applies to both TCP and QUIC, and you don't have to port from one to another and vice versa. So that truly is some great work.
Yeah. So I'll say,
I also wanted to add.
Go on, Robert.
I just wanted to add that the whole education use case and the fact that it's easier to experiment with these things is one of the reasons we did the QLog and the QVis as well. We originally tried to tweak the TCP congestion control stuff in the kernel, or at least try to figure out how that worked, and that's very difficult to even get out the current congestion window estimates and that kind of stuff. Even though it's now easier with eBPF. So that's definitely something that we foresee as one of the main use cases even for our tool in logging, is to enable students and newcomers to new companies and that kind of stuff to not only contribute new stuff, but also get up to speed much more quickly with what existing code is doing and how it performs in practice.
Yeah, I would say that there's actually that's one benefit that you just noted, Robin, that logging becomes much easier. Yes, with BPF it's there, but you can log a ton of things out of a user space implementation as well. However, I'll just say that we are past time, but we can continue. I think I don't want to speak for everybody here, but we can keep going. But we can call the tutorial officially over and just keep going here for as long as there's interest, I would say. And if you want to have chat, please go to the Slack channel, because once we close the Zoom window, your chat is going to be lost. Slack channel, however, it continues, so we can respond later and continue the discussions there. So if you want to have text conversation, do it on Slack. Yeah. There's somebody else who had a question. Sorry, go on, Ian.
I want to add something on that last point that Robin said, which is the QUIC did two things. One is it made transport encrypted. And so that meant that Wireshark, as it exists today with the raw PCAP, is much less useful in terms of transport information. However, that forced implementations to start exporting information from their implementations directly and from user space more widely. And that forcing function has turned out to be already quite a huge benefit, I think, to a variety of communities in terms of debugging and understanding congestion controllers and loss recovery and all of these things. And so I think even though it's sort of like by taking away something, we sort of caused people to build tooling that was much richer than was at least widely available when we started this whole thing. And I'll use the classic QUIC bug as my example of a major improvement to an existing algorithm that was made because we were exporting information from user space in QUIC, and Jana and I were there when we actually had an intern who added a new display view, like a table view, to our tracing tool, and suddenly we saw the congestion window skyrocket for no obvious reason, and we tracked it down to a many-year-old bug in QUIC that was due to them disabling slow start after idle, but not thinking through the full implications of that in a time-oriented congestion controller. So the moral of the story is I think the retransmit rate on the internet dropped like 15 or 20% when that was fixed. But this is what good tooling will do, and certainly all of Robin's work is good stuff, and will make congestion controllers of the future hopefully much better.
Indeed. Do we had more? Someone. Yeah, the floor's open, folks. There's still a lot of people here in the call.
I just want to say if there's someone who has a question for me specifically about the tooling or multiplexing and prioritization, maybe they should go first, because I'm slowly going to stop it here because it's like 11:30 here already.
Oh, come on, Robin. It's not that late. Sorry.
I still need to do some things.
I see Luca. Luca, do you want to say anything about Facebook and QUIC?
Yeah, I mean, I can. We have been working on QUIC since the beginning of the IETF standardization process. And at this point, like, how long has it been? Like 2.5 years, almost 3. Like, we have a large deployment at this point. And so this is something, that in the protocols world, that's like going from 0 to like full deployment in just a few years. It's something that like only QUIC made possible. Like, think about all the nice ideas around TCP that were impossible to deploy. And, now we have a lot more freedom to experiment. It's very powerful. That's what I want to say.
Awesome.
Thanks, Luca. By the way, that was not a sponsored plug.
No.
It was not a planned plug either. Okay, it seems like we are running out of energy here. It's been a long discussion, so maybe we can wind down here. I'll just say thank you everybody for being here. I hope this was useful. We are available in around different channels, email, various forums. Please reach out if you're working on QUIC. And I'd say that, as with any new protocol, and especially one as complicated as this, it is easy to lose yourself in the weeds, especially as documentation is a little bit sparse. And as that happens, that's going to be, that'll hopefully improve over time. But in the meantime, if you are trying to understand some aspect of QUIC, or you're trying to spend time, digging into some aspect of QUIC, shoot an email out to some of us, shoot an email out to the IETF QUIC working group, just to do a sanity check of if you're missing simple things that would help you understand something, before you start diving in deep. There's a lot of spaces here, I think, for people to explore. Robin's doing an excellent job of looking into the stream prioritization stuff. It's actually super ripe there for looking into. There's things about on the security. We, like I mentioned earlier, that this particular way that we're doing TLS and QUIC is kind of new. Even though there's been some security analysis, more is better in that space. So there's extensions, as we pointed out, that can be made more useful. So I would recommend that you look into those things, but at the same time also check and see if there have been, if there are things that you're missing before you really dive deep into this. But yeah, I guess that's about it from us, folks. Thank you so much, and hope this was helpful and meaningful to you.
Yeah, and definitely if there are questions you have that didn't get answered verbally, put them on Slack, and hopefully we will try to get them. But if not, maybe another QUIC member will get them.
Yeah, two plugs. One, Robin has a demo tomorrow of
Wednesday.
And Wednesday, you said. So please make sure to go see that. He's going to show more QUIC fun. And the second plug is on Friday, there's a workshop on EPIC, which is EPIQ, a QUIC-centered workshop on, I can't even remember what the acronym stands for, but it's things around QUIC. And Ian, I think you're doing the keynote there, aren't you?
I am. I'm going to be talking about QUIC CPU efficiency and optimizations and offloads. And
can you please do it in that hat? Can you please do it in that hat?
It's hair. It's actually 70s Peruvian rocker hair, sent to me by my boss, because there's not much fun anymore in the world of COVID.
Well,
but I thought it was appropriate in the Q&A section.
I think it's perfect. Yeah, I guess we've got EPIC and we've got this, so we've got a fair presence of QUIC here. Please go check out all of these things and ask us. And there's Ian's new baby.
Yep. Bye.
Thank you, folks. Thank you for the lovely discussion.
Thanks so much. Enjoyed it.
Thank you.
Thank you.